Picture this: two immense cities of stars, each one home to billions of suns, drifting silently toward one another across the vast, dark ocean of space. They move with a slowness that defies human comprehension, drawn together by an invisible force that has sculpted the universe since its earliest days. This is no catastrophic impact, no explosive crash as you might see in movies. Instead, it's something far more profound, a slow, stately, almost beautiful dance. A dance of galaxies. These cosmic encounters are among the most magnificent events in the universe, yet they unfold over timescales so immense that a single human lifetime is but a flicker in their story. Gravity acts as the choreographer here, pulling and shaping these colossal structures, weaving intricate patterns of starlight, gas, and dust across billions of years. What emerges from these mergers are not ruins, but new formations, tidal tails that stretch like celestial brushstrokes, rings of brilliant young stars, and galaxies reborn with entirely new identities. And within these transformations lie untold stories of stellar nurseries flaring to life, of black holes circling one another in a final embrace, and of elements essential for life being forged and scattered among the stars. In this video, we'll uncover the secret histories of these cosmic collisions. We'll explore how such encounters trigger furious waves of star formation, how they reshape galaxies into entirely new forms, and how they might even influence where life could arise in the universe. We'll journey from the mysterious role of dark matter, the unseen architect of these mergers, to the ultimate fate of our own Milky Way as it hurtles toward a future collision with the Andromeda galaxy. This is more than astronomy. It's a look into the evolving story of the cosmos itself, and by the end, I promise you'll never look at the night sky the same way again. So join me as we step into the grandeur and mystery of galaxies in embrace and uncover the hidden narratives written in the stars. To truly grasp the scale of these events, we have to step back and consider the sheer emptiness within a galaxy. A galaxy might contain hundreds of billions of stars, but the distances between them are so astronomically vast that the probability of any two stars actually colliding is almost zero. It would be like taking two handfuls of sand and tossing them into the air from opposite ends of a football field, hoping two individual grains will hit each other. The real action, the transformative drama, doesn't happen between the stars themselves, but within the vast clouds of gas and fine dust that drift in the spaces between them. This interstellar material is much more spread out, and when two galaxies begin to intermingle, these colossal gas clouds slam into each other. They don't just bounce off, they compress. This sudden, violent squeezing acts like a trigger, causing the gas to collapse under its own gravity. And in that collapse, millions of new stars can ignite at once in a brilliant, fiery burst of creation. The choreography of this dance is dictated entirely by gravity's invisible hand. It begins with a slow, almost imperceptible approach over hundreds of millions of years. As the galaxies draw nearer, their mutual gravitational pull starts to warp their shapes. Long, graceful arms of stars and gas are stretched out, forming magnificent structures known as tidal tails, celestial brushstrokes that can span hundreds of thousands of light years. We see this beautifully illustrated in a famous pair of interacting galaxies known as the Antennae galaxies, where two long, flowing tails of material extend far into space, giving them their insect-like name. This is the first dramatic act of the merger, a visible sign of the immense forces at play. As the interaction progresses, the galaxies may swing past each other, their momentum carrying them on long, looping orbits around a shared center of gravity. With each pass, they draw closer, their structures becoming more and more distorted and intertwined. This is where computer simulations become our most powerful time machine. By feeding the laws of physics into supercomputers, astronomers can fast forward through these billion-year processes. These simulations show us that the final act often involves the slow, inevitable spiral of the galaxy's cores toward each other. At the heart of most galaxies lies a supermassive black hole, and as the galaxies merge, these gravitational monsters are drawn together, destined to eventually orbit one another and merge in an event so powerful it ripples the very fabric of spacetime. The final products of these cosmic ballets are as varied as they are spectacular. Some mergers result in elegant ring galaxies, where a wave of star formation ripples outward like a pebble dropped in a pond. Others create massive, smooth, elliptical galaxies, the aging giants of the universe that have used up their gas and are filled with older, redder stars. Every collision is unique, influenced by the size of the galaxies, their angle of approach, and how much gas they contain. But each one leaves behind a fossil record in its structure, a story written in the motions of its stars and the distribution of its clusters. By learning to read this cosmic handwriting, we don't just see static islands of stars, we witness a universe in constant, dynamic, and beautiful motion. And yet, for all the graceful, almost serene beauty of this galactic dance, the most dramatic and transformative moments are born from pure, unadulterated violence. We shift our gaze from the grand, sweeping arcs of tidal tales to the chaotic, fiery hearts of the colliding galaxies themselves. This is where the mystery deepens, where we encounter the first great enigma of these cosmic encounters, the sudden, explosive ignition of starbursts. Think of it as the universe's most spectacular fireworks display, but on a scale so immense it defies belief. Within the relative calm of an isolated galaxy, star formation is a slow, steady process. But when two galaxies intertwine, that process is thrown into overdrive. The catalyst is the immense clouds of gas and dust, the raw material for building stars that fill the space between the stars. In a solitary spiral galaxy, this gas is often too diffuse, too spread out to collapse efficiently. But a galactic collision changes everything. It acts like a cosmic wrecking ball, sending violent shockwaves through these vast nebulae. The clouds don't just gently bump into each other, they slam together at tremendous speeds, creating regions of incredibly dense, incredibly compressed gas. This is the trigger. Under the immense pressure of these collisions, gravity gains the upper hand. Pockets of gas that were once stable suddenly cross a critical threshold. They begin to collapse inward, fragmenting into countless dense cores, and within each core, the temperature and pressure skyrocket until nuclear fusion ignites and a new star is born. But this isn't the birth of a single star, it's the simultaneous ignition of millions, even billions of them. The star formation rate doesn't just double or triple, it can skyrocket to hundreds of times what it was before. The galaxy, or at least the regions where this compression is most intense, becomes a stellar nursery operating at a frenzied, feverish pitch. We can see this phenomenon playing out in real time across the universe. A prime example is the pair of galaxies we call the Antennae, locked in a relatively early stage of their merger. To our telescopes, the regions where their gas clouds are colliding are not dark or quiet. They are ablaze with the brilliant blue-white light of countless newborn stars. These are massive, hot, and incredibly luminous stars living fast and dying young. Their intense ultraviolet radiation causes the surrounding gas clouds to glow in vibrant hues of pink and red, painting a picture of ferocious creative energy. These young stars are the markers of the starburst, a brilliant but short-lived phase in the merger's history. The aftermath of this stellar frenzy is just as important as the burst itself. Those massive blue stars don't last long. After only a few million years, a blink of an eye in cosmic terms, they exhaust their nuclear fuel and explode as spectacular supernovae. These explosions are the great recyclers of the universe. They blast outwards, spewing newly forged heavy elements like oxygen, carbon, silicon, and iron into the surrounding space. This enriched material gets mixed back into the remaining gas clouds, seeding them with the essential ingredients for rocky planets and, ultimately, the chemistry of life. A galactic collision, therefore, is not just a builder of stars, it is a factory for the very elements that make worlds like our own possible. The starburst is the fiery forge where the raw iron is cast, and the supernova are the hammers that scatter it across the cosmos. But here lies the central mystery that astronomers are still working to solve. What exactly dictates the intensity of this starburst? Why do some mergers produce a dazzling but brief flare of star formation, while others seem to sustain this heightened activity for much longer? The answers seem to lie in the intricate details of the collision, the amount of gas each galaxy had to begin with, the precise angle of their encounter, and the way gravitational forces channel and concentrate the gas flows. It's a complex cosmic feedback loop where the very stars being born can eventually shut down the process, as their winds and eventual explosions blow away the remaining gas, preventing further star formation. Unlocking the secrets of this regulation means understanding not just how galaxies interact, but how they live, breathe, and ultimately change each other on the most fundamental level. But for all the visible drama of colliding gas clouds and blazing starbursts, the true choreographer of this cosmic ballet remains utterly invisible. We now turn to the second profound mystery, one that underpins the very motion of the galaxies themselves, the enigmatic role of dark matter. Think of everything you can see in a telescope, every star, every nebula, every galaxy. Astonishingly, that familiar, luminous universe accounts for less than 15% of the total mass out there. The overwhelming majority, about 85%, is made of something we cannot see, touch, or directly detect: dark matter. This mysterious substance does not emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet we know it is there because of its immense gravitational pull. It is the hidden hand that guides the fate of galaxies, especially when they embrace. During a collision, the behavior of dark matter is utterly bizarre and completely counterintuitive. Picture two galaxies approaching one another. Their most prominent features, the sparkling spiral arms, the glowing gas clouds, are all made of what astronomers call baryonic or ordinary matter. As these two systems interact, their gas clouds slam into each other, creating the shock waves that trigger those spectacular starbursts. Their stars, while rarely colliding, are gravitationally pulled and twisted into those long, beautiful tidal tails. But the dark matter, it behaves differently. Each galaxy is embedded within a gigantic, diffuse sphere or halo of this invisible material. This halo is much larger than the visible galaxy itself. And because dark matter doesn't interact with itself or with normal matter through any force except gravity, these two vast halos can actually pass right through one another during a collision. There's no crashing, no slamming, no friction. It's a ghostly interpenetration, like two shadows merging and then separating. This strange behavior has a profound effect on the entire merger process. The gravitational pull from these massive, overlapping dark matter halos acts like an invisible glue and a guiding track. It helps hold the galaxies together even as the visible stars are being flung outward into streams. It dictates the trajectories the galactic cores will take as they swing around each other, ultimately determining the final shape of the merged galaxy. We can actually map the presence of this unseen material through a technique called gravitational lensing. The immense mass of a galaxy cluster, dominated by dark matter, warps the fabric of spacetime around it, bending the light from more distant galaxies behind it like a colossal lens. By studying this distorted light, astronomers can create a map of the mass distribution, revealing the outline of the dark matter halo. When we apply this to colliding systems, we get a glimpse of the hidden architecture guiding the entire event. A famous and stunning example of this is the Bullet Cluster. This isn't a single galaxy collision, but a collision of two entire galaxy clusters. Observations show a clear separation between what we can see and what we can infer. The visible gas from the two clusters detected in X-rays was slowed down and heated by the collision, lagging behind the galaxies. But the dark matter, mapped through gravitational lensing, continued on its path, perfectly aligned with the motion of the galaxies themselves. This provided some of the most direct evidence for the existence of dark matter and clearly demonstrated its non-interacting, ghost-like nature. It proves that what we see in a galactic merger is only a small part of the story. The real mass, the real gravitational engine, is operating from the shadows. This raises a host of compelling questions that astronomers are still working to answer. How does the distribution of dark matter within a halo influence the final structure of the merger remnant? Does a particularly dense or spread out halo lead to a more elongated or more spherical galaxy? And on the largest scales, how does the cosmic web of dark matter, the vast, invisible scaffolding upon which all galaxies are built, funnel these giants together in the first place? Understanding the role of dark matter is not just about solving one mystery of galaxy collisions. It is about deciphering the hidden framework of the entire universe. The visible splendor of colliding galaxies is merely the surface glitter on a deep, dark ocean of forces we are only beginning to comprehend. Now, as we peer deeper into the heart of this cosmic chaos, we encounter what is perhaps the most dramatic and enigmatic finale to any galactic embrace: the fate of the supermassive black holes that lurk at the very center of each galaxy. These are not merely large objects. They are gravitational behemoths, monsters with masses millions or even billions of times that of our Sun, residing in the central cores of nearly every large galaxy we have ever observed. Our own Milky Way hosts one named Sagittarius, a star, a relatively quiet giant. But in other galaxies, these black holes can be active, ferocious engines, powering brilliant quasars that outshine all the stars in their host galaxy combined. When two galaxies begin their slow dance, these central black holes are initially buried within their own galactic nuclei, separated by tens of thousands of light years. But gravity is a patient force. As the galaxies intertwine and merge, dynamical friction, a process where the black holes gravitationally scatter stars and gases, slowly but surely drains their orbital energy. They begin to sink, like two massive stones sinking through water, toward the new common center of gravity of the merged galaxy. This slow descent culminates in the formation of a binary black hole system, a pair of unimaginably dense objects now locked in a gravitational waltz of their own, orbiting each other. For a time, they can continue to spiral inward by flinging stars away through gravitational interactions, a cosmic game of billiards where the black holes trade orbital energy for the kinetic energy of the ejected stars. But eventually, they reach a critical separation of about 1 parsec, roughly 3.26 light-years, a distance known famously in astrophysics as the final parsec problem. This is the first great mystery of their fate. Why do many of these binary systems seem to stall at this distance? The theory suggests that at this point, they have effectively cleared out their immediate vicinity of stars to scatter. Without a mechanism to shed their remaining angular momentum, they might remain in a stable, billion-year orbit, never coming close enough to merge. The solution may lie in the presence of gas. If a large circumbinary disk of gas remains from the merger, its gravitational torques could provide the necessary drag to pull the black holes the final fatal distance together. Or perhaps the involvement of a third black hole from a previous, earlier merger could perturb the binary and kick it over the edge. This puzzle remains one of the most significant unsolved problems in galactic dynamics. Should they overcome this hurdle and continue their inward spiral, the final act is one of the most violent events in the universe since the Big Bang itself. When the black holes finally merge, they do not simply crash together quietly. Their merger sends powerful ripples through the very fabric of space-time itself, gravitational waves. These are not waves of light or matter, but literal distortions in the geometry of the cosmos, predicted by Einstein over a century ago, and only directly detected for the first time in 2015 by the LIGO Observatory from the merger of much smaller stellar mass black holes. The merger of supermassive black holes would generate gravitational waves of a much lower frequency, a deep, resonant thrum in the cosmic background that we hope to detect with future space-based observatories like the Laser Interferometer Space Antennae, or LISA. This event would release more energy in a fraction of a second than all the stars in the observable universe combined, a flash of pure gravitational energy that would literally stretch and compress everything in its path, though on a scale so minuscule we would never feel it. But the mysteries do not end with the gravitational wave signal. The merger process itself is incredibly complex. What happens to the surrounding environment? Some theories suggest that the merger can give the final black hole a powerful kick due to the asymmetric emission of those gravitational waves. This recoil could be so strong that it ejects the newly formed supermassive black hole entirely from its host galaxy at speeds of thousands of kilometers per second, sending it on a solitary journey through intergalactic space. Imagine that a galaxy without its central, defining heart. Alternatively, the violent merger could disrupt and scatter the innermost stars of the galactic nucleus or trigger a new, massive influx of gas onto the black hole, potentially igniting a brilliant quasar phase and profoundly affecting the future evolution of the galaxy. The dance of these black holes is far more than a final footnote. It is a transformative event that seals the fate of the merged galaxy, determining whether it will have a quiet future or an active, energetic one, and providing us with a unique laboratory to test the very laws of physics under the most extreme conditions imaginable. But this grand cosmic dance between galaxies, with its ghostly dark matter and its titanic black holes, ultimately leads to a profound and lasting transformation, the creation of an entirely new type of galactic architecture. Look up on a clear night and you might spot the Andromeda Galaxy, a classic spiral with its elegant arms winding out from a bright center. Now picture that beautiful structure and every star within it being utterly remade. What emerges from the chaos is something completely different, a vast, smooth, and almost featureless collection of stars shining with a soft, golden light. This is an elliptical galaxy, and it represents one of the most significant mysteries and outcomes of galactic collisions, the final, settled form of a cosmic embrace. These elliptical giants are the universe's retired aristocrats. They are dominated by older, redder stars, and they possess a serene, almost blurry appearance, lacking the distinct spiral arms or dusty disks of their younger counterparts. For a long time, astronomers wondered how such massive, amorphous structures could form. The leading theory, now strongly supported by evidence, is that they are the direct products of major mergers between spiral galaxies. Imagine two magnificent spiral galaxies, each with its stars orbiting in an orderly, rotating disk. When they collide, that orderly motion is completely disrupted. The gravitational forces during the merger are so violent and chaotic that they randomize the orbits of billions of stars. This process is poetically termed violent relaxation. It's not a gentle process. It's a gravitational upheaval that scatters stars into a new, three-dimensional spheroidal configuration, much like tossing a deck of cards into the air and watching them settle into a disordered pile. The original flat disk is gone forever, replaced by a swollen, roundish ball of stars. The transformation isn't just about the stars. Remember those brilliant starbursts triggered by colliding gas clouds? They play a crucial and final role in this metamorphosis. All that furious star formation consumes the vast reservoirs of cold gas at an incredible rate. Then, the subsequent supernova explosions from the short-lived massive stars act like a cosmic wind, blowing the remaining gas and dust clear out of the galaxy entirely. This double blow, rapid consumption and powerful expulsion, effectively quenches the galaxy. It starves it of the raw material needed to form new stars. The galaxy's stellar population slowly ages in unison, its blue stars flickering out first, leaving behind the longer-lived red stars to dominate the light. The galaxy, once a vibrant star-forming spiral, becomes a quiescent, red and dead elliptical. We can actually see this process frozen in various stages across the cosmos, providing us with a cosmic photo album of this incredible transformation. A perfect example is a galaxy known as NGC 7252, often nicknamed the Atoms for Peace galaxy. When we look at it, it's like seeing a galaxy caught in the act of becoming. It still possesses the spectacular, long tidal tails that are the hallmark of a recent collision, beautiful streamers of stars flung out by gravitational forces. But at its center, something new is emerging. The chaotic motions have begun to settle, and a large, smooth, and centralized glow is forming, the embryonic core of a new elliptical galaxy. It's a snapshot of a system midway through its billion-year makeover, a living fossil that shows us the bridge between the spiral we once knew and the elliptical it will become. Yet for all we understand, deep mysteries remain. Why is it that some major mergers seem to produce perfect ellipticals, while others leave behind a disordered mess or even a rejuvenated spiral? The answer seems to lie in the specific ingredients of the collision. The mass ratio of the two galaxies is critical. A merger between two equals, a major merger, is far more effective at completely destroying the original disks and creating a smooth elliptical. However, if a large galaxy consumes a much smaller one, a minor merger, it might just thicken the larger galaxy's disk or trigger a new wave of spiral arm formation without completely erasing its identity. The amount of gas present is another huge factor. A very gas-rich merger might lead to such an intense starburst that it completely exhausts its fuel and quickly becomes quiescent, forming a classic elliptical. A somewhat drier merger with less gas to begin with might not have the same explosive star formation, leading to a different outcome. Unraveling these nuances is what makes galactic astronomy so fascinating. It's not a single, simple recipe, but a complex cookbook where slight variations in ingredients create entirely different cosmic meals. This process reveals that collisions are not merely destructive. They are the universe's primary architects, building the diverse population of galaxies we see today from a few simple, initial blueprints. So if galaxy collisions are the great architects of the cosmos, why do we see such a stunning variety of structures in the night sky? Why is one galaxy a magnificent star-forming spiral while its neighbor is a smooth, quiescent elliptical? This brings us to one of the most fundamental and beautiful mysteries in all of astronomy, the origin of galactic morphology, the very shape and form of the galaxies themselves. It's a cosmic puzzle where the pieces are made of starlight, dark matter, and billions of years of history, and the guiding force that fits them together is the gravitational embrace between these island universes. Think of a galaxy not as a static painting but as a living, breathing entity with a life story. Its shape is its autobiography, a record of everything that has ever happened to it. A quiet, isolated existence might allow a galaxy to maintain its elegant spiral arms, a delicate balance of rotation and gravity, but a dramatic encounter, a close gravitational interaction with another galaxy, can rewrite that story entirely. The outcome of that encounter depends on a cosmic roll of the dice, the angle of impact, the relative speeds involved, and perhaps most importantly, the sizes of the dancers. A near miss, a gravitational glancing blow, can actually enhance a galaxy's spiral structure. The tidal forces pull on the disk, triggering instabilities that amplify the arms, making them more prominent and even inducing the formation of a central bar, a straight lane of stars cutting through the nucleus. It's as if the gravitational perturbation gives the galaxy a shake, and the resulting ripples settle into a new, but still recognizable, spiral pattern. On the other end of the spectrum, a head-on collision between two giants of roughly equal size, a major merger, is a truly transformative event. This is the process that, as we discussed, can completely erase the ordered structure of two spiral disks and forge a new elliptical galaxy from the chaos. The beautiful symmetry is destroyed, replaced by a random swarm of stars, but the universe is rarely so simple, and the real mystery deepens when our observations contradict our elegant computer models. We find galaxies that, by all accounts, should have been completely disrupted by past collisions. Their stellar halos are littered with the fossilized debris of consumed companions, clear evidence of a violent history of cannibalism. And yet there they are, proudly displaying a gorgeous, well-defined spiral structure. How did they survive? How did they regenerate their majestic disks after such a traumatic event? The answer may lie in a continuous inflow of fresh, cold gas from the cosmic filaments that feed galaxies. This pristine fuel, raining down from intergalactic space, could steadily replenish the disk, allowing it to reform and maintain its spiral identity even after a significant merger. It's a testament to the resilience of some galaxies, their ability to heal from cosmic wounds and continue their star-forming lives. To unravel these histories, astronomers must become cosmic detectives, piecing together clues from a variety of evidence. They study the motions of stars, the galaxy's kinematics, looking for the subtle twists and turns that betray a past interaction. They analyze the chemical composition of stars, their metallicities, because a sudden influx of new elements can mark the timing of a merger that triggered a starburst. They even look for groups of stars that move together on unusual orbits, the surviving cores of long-ago devoured dwarf galaxies. This detective work reveals that galactic morphology is not a simple either-or proposition. It's a spectrum, a rich tapestry woven from threads of isolation, interaction, and outright collision. A galaxy's shape is a moment frozen in time, a single frame in a billion-year movie. The same galaxy might be a spiral today, become an irregular mess during a collision tomorrow, and finally settle into an elliptical eons from now. These galactic embraces are the universe's ultimate creative and destructive forces. They can tear down old structures with unimaginable violence, but from that chaos, they can also build new forms of breathtaking beauty and complexity, endlessly weaving the grand tapestry of the cosmos. But as we marvel at these grand architectural transformations happening on a galactic scale, it's impossible not to wonder about the smaller, more intimate stories playing out within them. What happens to the individual planetary systems, the potential cradles of life, when their host galaxy undergoes such a violent merger? This brings us to a mystery that touches on our very place in the cosmos, the impact of these colossal collisions on habitable zones and the potential for life itself. We often picture a planet's habitability as being determined by its distance from its star, that Goldilocks zone where water can remain liquid, but this is only part of the story. A planet's entire galactic neighborhood plays a crucial role, and when two galaxies collide, that neighborhood can be turned utterly upside down. The first thing to understand is that space is overwhelmingly empty. Even during the most dramatic galactic merger, the chance of two stars actually colliding is astronomically low. The real danger isn't direct impact, but the immense gravitational chaos that ensues. As the galaxies intertwine, their combined gravitational field becomes a turbulent sea. Stars and their planetary entourages are no longer on stable, predictable orbits. They can be flung onto wildly new paths, some thrown out on long, eccentric orbits that plunge them dangerously close to the galactic center, a region teeming with radiation from the supermassive black hole and densely packed stars. Even worse, some stars can be given such a strong gravitational kick that they are ejected entirely, hurled out into the freezing, dark emptiness of intergalactic space, their planets forever cut off from the light and warmth of any other star. For any life on those worlds, it would be a death sentence, a slow, deep freeze into eternal night. Yet, for all this destructive potential, these cosmic encounters might also be incredible engines of creation and enrichment. Remember the intense starbursts we discussed, those brilliant waves of new star formation. While they produce deadly supernovae, they also forge and spread the heavy elements essential for life as we know it: carbon, nitrogen, oxygen, phosphorus. A planetary system that forms from gas enriched by a past merger might be far more likely to have the necessary ingredients for rocky planets and complex chemistry. It's a cosmic paradox. The same event that can sterilize one world might provide the fundamental building blocks for life on another. A planet orbiting a star born from the ashes of a supernova triggered by a collision could be seeded with a richer abundance of these vital elements from the very beginning. This creates a complex and fascinating balance that astrophysicists are only beginning to model. On one hand, you have the gravitational disruption that can destroy stable, life-friendly environments. On the other, you have the chemical enrichment that might make life more likely to arise in the first place. Which force wins out? Does the net effect of galaxy mergers increase or decrease the number of habitable worlds in the universe? The answer is likely not simple. It might depend on a planet's location within the galaxy during the collision, the timing of the merger in the galaxy's history, and even the type of life we're considering. Perhaps simple microbial life could survive the increased radiation from temporary starbursts, while more complex organisms could not. This forces us to expand our view in the search for life beyond Earth. We must consider not just a planet's immediate environment, but the entire history of its galaxy. The most life-friendly corner of the cosmos might not be a quiet, unchanging spiral arm, but a region that experienced a carefully timed merger, one that provided the enrichment for life without the gravitational violence to tear it all apart. The secret history of our own solar system's elements suggests we may all be children of such a violent and creative cosmic past. But to truly grasp the rhythm of these cosmic encounters, we must step back and ask a fundamental question: how often do these galactic dances actually happen? This is the mystery of timing and frequency, a puzzle that requires us to look across the vast expanse of cosmic history. The universe today is a sprawling, expanding place, but it wasn't always so. In its youth, the cosmos was far more crowded and chaotic. Billions of years ago, galaxies were significantly closer together, packed into a smaller volume of space. This simple fact of cosmic geography means that galactic collisions were once a far more common occurrence, a regular feature of the early universe's tumultuous adolescence. Grand mergers were not rare, special events. They were part of the standard process of galactic growth and evolution, the primary way galaxies built themselves up from smaller building blocks. We can peer back into this busier past thanks to incredible instruments like the Hubble Space Telescope. Its iconic ultra-deep field image is more than just a beautiful tapestry of faint lights. It's a core sample drilled deep into time itself. By staring at a seemingly empty patch of sky for days on end, Hubble revealed thousands of the most distant galaxies ever seen, their light having traveled for over 13 billion years to reach us. Within this deep time portrait, astronomers can perform a kind of cosmic census. They meticulously count the number of galaxies that appear distorted, connected by bridges of light, or otherwise engaged in gravitational duets. By comparing the fraction of interacting galaxies at different distances, and therefore different eras, they can statistically estimate the merger rate and how it has evolved over the eons. The conclusion is clear. The universe was a much more sociable and collision-prone place in its distant past. However, counting cosmic crashes is fraught with difficulty and uncertainty. One of the biggest challenges is a simple trick of perspective known as a projection effect. From our vantage point on Earth, we see the universe in two dimensions. Two galaxies might appear to be very close together, perhaps even touching in our telescope's image. In reality, they could be separated by millions of light years along our line of sight, completely independent of one another and not interacting at all. It's like seeing two fireflies in the night sky. They might look like they're right next to each other, but one could be in your backyard and the other in a field miles away. Distinguishing these false pairs from genuine, gravitationally bound couples requires painstaking follow-up observations to measure their precise distances, a time-consuming process that adds layers of complexity to the statistics. Furthermore, identifying a merger in its very earliest stages is incredibly difficult. The first gravitational flirtations between two galaxies, before they've developed dramatic tidal tails or stirred up brilliant starbursts, produce only subtle distortions in their shapes. Detecting these faint whispers of an impending collision requires extremely sensitive instruments and advanced image analysis techniques. This means our current merger rate estimates might still be missing a significant number of these embryonic interactions, subtly skewing our understanding of the true timeline. The environment a galaxy lives in also plays a huge role. In the dense, crowded neighborhoods of galaxy clusters, close encounters and mergers are a regular fact of life, happening with far greater frequency than in the vast, empty deserts of cosmic voids. A galaxy's address within the large-scale structure of the universe profoundly influences its social life and its likelihood of a dramatic embrace. Untangling this mystery is absolutely essential because the collision rate is more than just a number. It's a fundamental clock that ticks to the rhythm of cosmic evolution. The frequency of these events dictates how quickly galaxies can grow, change their shape, and build up their central black holes. By pinning down the precise timing and rate of mergers throughout history, we are essentially writing the biography of the universe itself, reconstructing the assembly history of everything we see. It connects the grand, overarching architecture of the cosmic web directly to the intimate, life-altering stories of individual galaxies. revealing a universe that is constantly being remade through a slow, stately, and breathtakingly beautiful dance of giants. While the gravitational chaos and stellar fireworks of a galactic collision are spectacular to behold, they are also the engines of a far more fundamental process, the cosmic distribution of the very elements that make up our world and ourselves. This brings us to our eighth mystery, one that touches on our own origins, the profound chemical enrichment that spills forth from these violent embraces. Think of it this way: when two galaxies merge, they don't just mix stars, they become vast, chaotic factories, forging and scattering the heavy elements essential for planets and life across incredible distances. The raw materials for this factory are the immense clouds of primordial hydrogen and helium that have filled galaxies since their birth. On their own, these clouds are relatively pristine, simple. But within them, nestled like tiny islands, are the enriched remains of stars that have already lived and died ash from previous generations of supernova, laced with elements like carbon, oxygen, nitrogen, and iron. A galactic collision acts like a colossal blender set to its highest setting. As the gas clouds from each galaxy slam into one another at tremendous speeds, they create powerful shock waves. These shocks do more than just compress gas to form new stars. They violently stir the mixture, churning these enriched pockets of heavy elements and spreading them throughout the merging system, and often far beyond into intergalactic space. This process, known chemically as pollution, is the universe's way of recycling its building blocks on a truly grand scale. The consequences of this elemental redistribution are staggering. A new generation of stars born from this enriched gas will inherently contain a higher metallicity, a higher proportion of elements heavier than hydrogen and helium. This isn't just a minor detail, it fundamentally changes the star's properties and the planetary systems that may form around it. Stars with higher metallicity tend to have stronger stellar winds and different lifespans. More importantly, planets forming around such stars have a much richer supply of raw materials. Elements like carbon and oxygen are the bedrock of rockier terrestrial planets. Silicon and iron form planetary cores. The presence of these metals dramatically increases the likelihood of forming rocky worlds in the habitable zone, planets like our own Earth. Furthermore, this enriched gas also contains the essential ingredients for life as we know it: phosphorus for our DNA, nitrogen for our proteins, and oxygen for the water we drink. A galactic collision, therefore, can seed entire regions of space with the potential for life, turning a relatively barren area into a fertile galactic nursery. Yet, for all its importance, tracking the precise flow of these metals is one of the most daunting challenges in modern astrophysics. The ejected material doesn't travel in a simple, uniform wave. It gets channeled by magnetic fields, heated by radiation from newborn stars, and twisted by unimaginable turbulence. To map this flow, astronomers must become cosmic chemists, using powerful tools like high-resolution spectroscopy. By analyzing the faint light from distant galaxies, they can detect the unique fingerprint of specific elements, the telltale sign of iron or oxygen in a stream of gas, and measure not only its composition but also its velocity and direction. This allows them to trace these enriched winds as they blow out of the galaxy. However, these observations only provide a single snapshot. To understand the full story, scientists must create incredibly sophisticated computer simulations that model the complex physics of these chaotic environments, from magnetohydrodynamics to radiative transfer. It is a painstaking process of comparing virtual universes to real ones, slowly refining our models to match the faint chemical signatures we detect. This grand cycle of creation and dispersal connects us directly to these cosmic events. Every atom of oxygen we breathe, every particle of iron in our blood, Every atom of calcium in our bones was forged in the heart of a massive star that lived and died long before our sun was born. That star's explosive death scattered these elements into space, where they became part of a vast interstellar cloud. It is highly likely that the gravitational shockwave from a past galaxy collision, perhaps even the merger that helped form our own Milky Way, helped compress that cloud and trigger the formation of our solar system. We are quite literally the children of stars and the beneficiaries of ancient cosmic violence. The story of a galactic collision is therefore not just a tale of distant giants. It is our own origin story, written in the elemental language of the universe, waiting for us to decipher its secrets. And just as a violent storm at sea leaves behind scattered driftwood and smooth sands as evidence of its passing, so too do galaxy collisions leave behind enduring monuments in the stars. These are not the brilliant starbursts or the swirling chaos of the merger itself, but rather the faint, ghostly echoes that can persist for billions of years after the main event has concluded. They appear as delicate shells of stars, great looping arcs, and vast, sweeping tidal tails that stretch far beyond the main body of the merged galaxy. These structures are the silent witnesses, the fossilized evidence of a monumental gravitational encounter, and deciphering their language is a primary tool of cosmic archaeology. To understand how these beautiful features form, we need to think about the individual stars within a galaxy. In a stable, isolated system, each star is on a stable orbit, held in a delicate balance by the combined gravity of all the other stars, gas, and dark matter. But when another galaxy comes calling, that gravitational balance is violently disrupted. It's not a smooth, uniform pull, it's a complex, shifting tidal force. As the two galaxies pass through or near each other, the gravitational pull on the stars closer to the intruder is stronger than on those farther away. This difference in force, this tidal pull, acts to stretch the galaxy. For some stars, this provides just enough of a gravitational nudge to fling them out of their original orbits entirely. They aren't destroyed, they are instead stripped away from their parent galaxy and placed onto vast new trajectories that carry them far out into the halos of the merging system. The specific geometry of the collision then imprints itself onto these exiled stars. In a relatively head-on collision, stars can be pulled out and then fall back in, oscillating in and out like stones dropped into a pond. The points where they slow down and reverse direction create regions of higher density, appearing to us as those delicate, concentric shells of light nested around the central galaxy. It's a phenomenon akin to a gravitational sonic boom. In a more glancing encounter, the tidal forces can draw out long, graceful streams of stars' tidal tails that often curve away from the galactic cores, sometimes connecting the two galaxies like a luminous bridge before they finally merge. These tails can span hundreds of thousands of light years, serving as the most dramatic and visible signposts of an ongoing interaction. The true power of these features lies in their longevity. While the brilliant blue light of starbursts fades after a few 100 million years as the most massive stars explode, these shells and tails, made of billions of longer-lived stars, can endure for many billions of years. This makes them an incredible historical record. By meticulously mapping their structure, density, and the motions of the stars within them, astronomers can work backwards like detectives at a crime scene to reconstruct the event that created them. The number of shells can hint at the number of pericenter passages, how many close approaches the galaxies made before finally merging. The shape and curvature of a tidal tail can reveal the angle of the initial impact and the relative masses of the two galaxies involved. A galaxy surrounded by multiple, complex sets of shells might be telling us the story of not one, but several distinct merger events throughout its long history, a palimpsest of past collisions written in starlight. However, reading this cosmic book is not without its challenges. While our computer simulations have become incredibly sophisticated, often able to recreate the general appearance of these tidal features, matching a specific simulation to a specific real-world galaxy often reveals subtle discrepancies. The shells might be thicker or more numerous than predicted, or the tails might curve in an unexpected way. These mismatches are not failures. They are clues pointing to the complexities we are still working to include in our models. They might be telling us that the dark matter halo of the galaxy has a different shape than we assumed, or that the original galaxies had more gas, whose gravitational influence and subsequent expulsion altered the stellar dynamics. Perhaps the merger happened more recently or longer ago than our initial estimates suggested. Each faint loop of stars is a sentence in a galactic autobiography, and by learning to read its unique grammar, we are slowly piecing together the secret histories of these majestic cosmic embraces, uncovering stories of violence and beauty written across the expanse of deep time. Yet for all the intricate details of their dance, no two galaxy collisions are ever truly identical. Their story is not written solely by the galaxies themselves, but also by the neighborhood they live in, the vast and varied environments that make up the cosmic landscape. Just as a quiet country town fosters a different kind of life than a bustling, dense metropolis, the specific address of a galaxy within the universe profoundly shapes how it interacts with its neighbors and the ultimate outcome of those encounters. This is the mystery of galactic environment, a reminder that these majestic embraces do not happen in a vacuum, but are instead orchestrated by the largest structures in existence. The universe is organized into a magnificent web-like pattern, with galaxies congregating in clusters and groups that are connected by long, thin filaments of dark matter and gas, the cosmic web. Where a galaxy resides on this web dictates its social life. Imagine a massive, dense city of galaxies, a cluster containing thousands of members all buzzing around a common center at incredible speeds. In this urban cosmic environment, a galactic collision is less like a slow, graceful waltz and more like a chaotic, high-speed traffic jam. The galaxies are so close together that they don't often have time for a prolonged, merging embrace. Instead, they experience rapid, frequent gravitational encounters known as harassment. These are high-speed flybys where galaxies zip past each other, their gravitational fields briefly tugging and distorting one another before they continue on their way. This constant jostling can still have a dramatic effect, puffing up galactic disks, triggering bursts of star formation, and slowly stripping away their outer layers of stars and gas over billions of years. It's a form of evolution driven by relentless, fast-paced interaction. Contrast this with a quieter suburban setting, a galaxy group. Our own Milky Way is part of such a group, the local group, which contains about 54 galaxies, with Andromeda and ourselves as the two largest members. Here, the environment is far less crowded. The distances between galaxies are greater, and their relative speeds are much slower. This allows for the kind of slow, deliberate gravitational dance we've been describing. In a group, two galaxies can become gravitationally bound, their slower speeds allowing them to fall into each other's embrace and eventually merge over billions of years. The slower, more intimate mergers possible in these environments are the primary architects of the large elliptical galaxies we see today, as they have the time to completely combine and relax into a new form. But the environment exerts its influence in more ways than just gravity. Galaxy clusters are not empty, they are filled with a seething, hot soup of gas known as the intracluster medium. This gas can be tens of millions of degrees, and it poses a serious threat to any galaxy passing through it, especially one already engaged in a collision. As a gas-rich spiral galaxy moves through this hot medium, it experiences a powerful wind, much like a bicyclist feeling the push of a strong headwind. This process, called ram pressure stripping, can violently tear the cold gas right out of the galaxy. For a colliding system, this external force can be decisive. It can rob the galaxies of the very fuel needed to power the brilliant starbursts that normally define a merger, effectively quenching star formation before it even really begins. The resulting merged galaxy might be left gas-poor and quiescent far earlier than if it had collided in the isolation of a group, its story of creation cut short by its harsh surroundings. Unraveling this complex interplay requires astronomers to become cosmic cartographers on a grand scale. They must conduct enormous surveys of the sky, painstakingly mapping the positions and motions of millions of galaxies to understand the architecture of the cosmic web. Only by seeing the big picture can they then understand the small-scale drama of individual collisions. It's a daunting task, as it means we must study not only the galaxies themselves, but also the seemingly empty space around them, which is in fact filled with invisible dark matter and seething hot gas that silently guide their evolution. The secret history of a galactic collision is therefore a tale told on multiple scales, from the intimate dance of two partners to the immense, overarching framework of the universe itself, proving that every celestial event is connected to the grand cosmic design. Yet amidst the gravitational chaos and stellar fireworks, another even more violent phenomenon can be unleashed from the very heart of the merging galaxies, the awakening of a dormant cosmic monster. At the center of most large galaxies, including our own Milky Way, lies a supermassive black hole, a gravitational titan with an appetite for matter. For much of its life, this beast may slumber quietly with little material to consume, but a galactic collision can change everything, potentially triggering an outburst of energy so fierce it can outshine every single star in the galaxy combined. This is the mystery of the active galactic nucleus, or AN, and it represents one of the most dramatic and explosive chapters in the story of cosmic collisions. The basic recipe for awakening this monster seems straightforward. A supermassive black hole needs fuel. In the serene environment of an isolated spiral galaxy, the gas needed to feed it might be orbiting peacefully in the disk, too far out and too stable to fall inward. A galactic merger acts like a cosmic stir-fry, violently churning the galaxy's structure. Vast reservoirs of gas that were once placid are suddenly shocked, compressed, and thrown into disarray. This chaos can rob the gas of its orbital energy, allowing it to fall inward toward the waiting gravitational abyss. As this material spirals down toward the event horizon, it forms a superheated, glowing disk of plasma, an accretion disk. The friction within this disk is so intense that it heats the material to millions of degrees, causing it to radiate tremendous energy across the entire electromagnetic spectrum, from X-rays to radio waves. In the most extreme cases, this process creates a quasar, a beacon of light so luminous it can be seen clear across the observable universe. This is where the mystery deepens. If the connection were simple, every major galaxy merger would ignite a brilliant quasar at its core, but our observations reveal a far more puzzling reality. Powerful space telescopes like Chandra and Hubble have peered into the hearts of countless colliding galaxies, and they show us a mixed picture. Some merging systems, like the famous Antennae galaxies, are undergoing tremendous starbursts, yet their central black holes remain surprisingly quiet. Other galaxies, like NGC 6240, showcase not one but two bright, active nuclei, the supermassive black holes from each progenitor galaxy, both feasting on the gas delivered by the collision and blazing with X-rays before they eventually merge themselves. And then there are quasars that appear to be living in perfectly normal, isolated galaxies with no obvious signs of a recent collision at all. This tells us that the simple presence of gas is not enough. The delivery mechanism is everything. The gas must lose nearly all of its angular momentum to fall all the way to the black hole's event horizon, and different mergers may accomplish this with varying efficiency. The timing of the influx is also critical. A huge dump of gas all at once might actually choke the accretion process, smothering the black hole instead of feeding it in a steady stream. Alternatively, the geometry of the collision might be the deciding factor. A direct head-on impact could send gas flooding directly toward the center, while a more glancing blow might only perturb the outer disk without effectively funneling material all the way to the core. It's also possible that the black hole itself plays an active role in shutting down its own food supply. The immense radiation and powerful jets blasting out from an active nucleus can create a feedback loop, heating and pushing away the surrounding gas and effectively starving the black hole of further fuel, limiting the duration of its brilliant outburst. Solving this mystery is crucial because it reveals how these supermassive black holes grow to such immense sizes and how they, in turn, shape the evolution of their host galaxies. This process of AGN feedback is now considered a fundamental force in galactic evolution. The energy pouring out from an active nucleus can regulate star formation by heating and dispersing galactic gas, effectively deciding whether a galaxy continues to create new stars or is forced into a quiet retirement. The awakening of these cosmic monsters during a collision is therefore not just a spectacular side effect. It is a pivotal moment that can determine the ultimate fate of the entire galaxy, a testament to the profound interconnectedness between a black hole and its stellar home. But while the titans of the cosmos, the massive spirals and ellipticals, engage in their slow, dramatic dances, there is an entire population of smaller, often overlooked participants in these galactic encounters, the dwarf galaxies. These diminutive collections of stars, gas, and dark matter are the most common galaxies in the universe, yet they exist in a perpetual state of vulnerability, especially when a larger galaxy decides to tango. In the violent gravitational turbulence of a major collision, you would expect these cosmic minnows to be utterly annihilated, either ripped apart by tidal forces or completely absorbed and assimilated by their gigantic partners. Yet, when we survey our local universe, we find a bustling population of dwarf galaxies thriving in groups and clusters, orbiting larger galaxies like bees around a hive. Their persistent presence against seemingly impossible odds presents a fascinating mystery. How do the smallest galaxies survive the cosmic chaos? The secret to their resilience appears to be a combination of stealth, armor, and sometimes a surprising origin story. For some dwarfs, the key is simply staying out of the way. A dwarf galaxy on a wide, stable orbit around a larger host can spend billions of years circling at a safe distance, like a moon orbiting a planet, only occasionally feeling the faintest gravitational tug from the main event unfolding far below. It can essentially wait out the storm, avoiding the intense gravitational shocks and tidal forces that would spell its doom if it ventured too close to the chaotic merger zone. This strategy of maintaining a respectful distance allows it to preserve its identity and structure across eons. For other dwarfs, survival is not about evasion but about inherent toughness. Many of these small galaxies are thought to be absolutely dominated by their dark matter content. While a large spiral like the Milky Way has a massive dark matter halo, the density of that halo is relatively low because it's spread out over such a vast volume. A dwarf galaxy, however, can have an incredibly dense, compact dark matter halo that acts like a suit of powerful gravitational armor. This dense, invisible core holds the galaxy's stars together with an iron grip, making it far more difficult for the tidal forces of a larger passing galaxy to pull it apart. It's the difference between trying to rip apart a solid rock and a loose cloud of dust. The dwarf's dark matter provides the structural integrity to withstand the gravitational onslaught. Perhaps most intriguingly, some dwarf galaxies aren't survivors of the collision at all, they are its children. During a violent merger between two large galaxies, vast streams of gas and stars are pulled out into those magnificent tidal tails. Within this ejected material, the local density can sometimes be high enough for gravity to take over, causing the stream to fragment and collapse into new, gravitationally bound objects. These are not the majestic spirals of their progenitors, but small, irregular collections of stars born from the debris of the collision itself. These tidal dwarf galaxies, as they're called, are fascinating because they are born from the recycled material of their parents and are largely devoid of the dark matter that protects their primordial cousins. Their survival is tenuous, but they represent a second-generation population of galaxies, a direct and beautiful consequence of cosmic violence. Furthermore, an interaction with a giant neighbor isn't always a death sentence. It can sometimes be a catalyst for renewal. The gentle gravitational nudge from a passing galaxy, even if it isn't a full-blown collision, can compress the gas within a dormant dwarf galaxy, triggering a wave of new star formation. This can cause the entire dwarf to light up with the brilliant blue glow of young stars, effectively resetting its evolutionary clock and making it appear younger and more vibrant than it actually is. This process allows the dwarf to have its own unique story of transformation, independent of the fate of the larger galaxies it accompanies. The survival and evolution of dwarf galaxies add a crucial and nuanced subplot to the grand narrative of cosmic collisions. They demonstrate that in the galactic arena, size isn't everything. Strategy, inherent strength, and sometimes just being in the right place at the right time can allow even the smallest players to endure the universe's most dramatic events. While gravity is the undeniable choreographer of the galactic dance, and dark matter its invisible stage, there is another, far more subtle force at play within these colliding titans, one that weaves through the very fabric of space between the stars, influencing events on every scale. This is the enigmatic role of magnetic fields, a pervasive but often overlooked player in the drama of cosmic collisions. We tend to think of space as a true vacuum, utterly empty, but it is in fact threaded with invisible lines of magnetic force that originate from the motions of charged particles within the interstellar gas. These fields are incredibly weak by Earth standards, millions of times fainter than a common refrigerator magnet. But across the vast volumes of a galaxy, their influence becomes significant, guiding the movement of cosmic rays and shaping the behavior of the gas clouds that are the lifeblood of star formation. When two galaxies merge, this magnetic tapestry is thrown into unimaginable turmoil. The same colossal forces that wrench out tidal tails and compress gas clouds also stretch, twist, and amplify these magnetic fields. Think of it like pulling on a bundle of elastic bands. The lines of force get stretched tighter and become more powerful. Turbulence from colliding gas clouds and shear flows from the galaxies spinning past one another act as a natural dynamo, potentially strengthening these fields by a factor of 10 or even 100. This transformation turns the magnetic field from a passive backdrop into an active participant in the merger, capable of exerting its own pressure on the surrounding environment. It can resist the gravitational collapse of gas clouds, potentially putting a brake on the very star formation that the collision is trying to trigger. or it can channel and focus flows of material, funneling gas efficiently toward the waiting supermassive black holes at the galactic centers. The real mystery lies in predicting which of these roles the magnetic field will play in any given collision. In some scenarios, a well-ordered magnetic field might act like a scaffolding, providing support to a massive gas cloud and preventing it from fragmenting too quickly, allowing it to collapse into a single, monstrous star instead of many smaller ones. In other cases, these amplified fields could help launch and collimate the powerful galactic winds that blow out of merging systems, acting like the barrel of a cosmic cannon to direct enriched material far out into intergalactic space. Conversely, if the field becomes too strong and chaotic, it might provide too much resistance, effectively propping up gas clouds and preventing them from reaching the densities needed to ignite new stars at all. The outcome likely depends on the initial strength and geometry of the fields in each galaxy and how they are twisted by the specific dynamics of the encounter. Unraveling this complex magnetic influence is a formidable challenge because we cannot see these fields directly. To map them, astronomers must use specialized radio telescopes equipped with polarimeters. These instruments detect the faint radio waves emitted by electrons spiraling along the magnetic field lines. The polarization of this light, the specific direction in which its waves vibrate, betrays the orientation of the invisible field itself. It's a bit like looking at the pattern of iron filings around a magnet to deduce its shape, but across distances of millions of light years. So far, only a handful of nearby merging galaxies have been studied in this kind of detail, and each one reveals a unique and complex magnetic personality, suggesting that we have only begun to scratch the surface of this hidden dimension. Understanding the role of magnetism is not just an academic exercise, it is essential for creating a complete and accurate picture of galactic evolution. Our most sophisticated computer simulations of galaxy collisions have historically focused on gravity, hydrodynamics, and radiation. Only recently have they begun to incorporate the effects of magnetic fields, and the early results show that they can alter the outcome in significant and unexpected ways, changing the timing of starbursts and the structure of the resulting galaxy. This secret force reminds us that the universe is a multi-layered puzzle, where gravity may set the grand stage, but other actors like the subtle, pervasive pull of magnetism write crucial parts of the script, adding a profound and beautiful complexity to the secret histories of cosmic collisions. Amid the chaos of colliding gas clouds and the brilliant firestorms of new stars, galaxy mergers forge some of the most enduring and exquisite structures in the entire cosmos: globular clusters. Imagine a dense, shimmering sphere containing 1,000,000 stars, all bound together by gravity in a space so tight that the night sky from a planet within it would be a perpetual, dazzling twilight. These ancient relics orbit galaxies like swarms of stellar bees, and their origins have long been a puzzle. While some may be primordial, dating back to the earliest days of the universe, a growing body of evidence suggests that the violent, fertile conditions of a galactic collision are a perfect crucible for creating new generations of these magnificent clusters. The recipe for a globular cluster demands extreme conditions, unimaginable pressure and density within a giant molecular cloud. In the calm of an isolated galaxy, such environments are rare. But when two galaxies intertwine, they create exactly the kind of cosmic pressure cooker required. The colossal shock waves from colliding gas clouds act like a universal forge, compressing these nebulous regions to densities thousands of times greater than normal. Within these crushed, turbulent pockets, gravity gains an overwhelming advantage, causing the entire cloud to collapse not into a few stars, but into a single massive event, the simultaneous birth of hundreds of thousands or even millions of stars all at once. This isn't just a star cluster, it's a supercluster born in a single, furious burst of creation. Its stars all siblings from the same violent natal moment. We can see this process happening in real time by looking at galaxies currently undergoing mergers. The Antennae galaxies are perhaps the most spectacular laboratory for this phenomenon. Within the overlapping regions where their gas clouds are slamming together, astronomers have identified dozens of brilliant blue knots of light. Each one is a young massive cluster, a grouping of stars so densely packed that from a distance it appears as a single blazing point. These clusters are incredibly luminous, hot, and massive, containing the equivalent of millions of suns worth of material. They are, in every way, the infant prototypes of the globular clusters we see orbiting older, quieter galaxies. They are globular clusters in the making, caught at the very moment of their birth, giving us an unprecedented window into a process that was once thought to have ended billions of years ago. The great mystery, however, is not just their formation but their survival. The early life of one of clusters is incredibly perilous. The very same starburst that gave it life also surrounds it with danger. The intense radiation pressure from its own massive, young stars can theoretically blow the cluster apart from the inside before it ever has a chance to settle down. Even if it survives this initial feedback, it must then run a gauntlet of external threats. The tidal forces within a newly merged galaxy are chaotic and extreme. A cluster on an unfortunate orbit can be stretched and ripped apart by the shifting gravitational potentials, its stars scattered into the galactic halo. Furthermore, the cluster must survive any subsequent bursts of activity from the galactic nucleus or additional mergers that could disrupt its fragile gravitational binding. The question is, what allows one cluster to endure for 10 billion years while another, seemingly identical one, is dismantled in just a few 100 million? The answer may lie in a critical escape. Many of the young massive clusters we see in mergers are still deeply embedded within the gas clouds that formed them. Their fate may be determined by how quickly they can expel this leftover gas. If the cluster can efficiently clear its surroundings through stellar winds and supernova explosions, its stars will settle into a stable, tightly bound gravitational system. This process also involves a kind of natural selection based on mass. The most massive clusters, with their incredibly deep gravitational potential wells, are far better at holding onto their stars against external tidal forces and internal disruptions. They have the gravitational muscle to survive. The lighter clusters are more vulnerable and may be the ones we see being torn apart, their stars contributing to the diffuse light of the galactic halo. This suggests that the glorious globular clusters we see today are the cosmic equivalent of champions, the strongest and most massive survivors of a brutal evolutionary contest that began in a frenzy of colliding gas and ancient violence. This connection provides a profound link across cosmic time. It ties the most violent, energetic events in the modern universe, galaxy collisions, to the oldest, most serene structures we can observe. Each ancient globular cluster orbiting our Milky Way could be the silent, enduring remnant of a dramatic merger that occurred in our galaxy's wild youth, a fossilized echo of a long-ago galactic embrace. By studying the young clusters in current mergers, we are effectively reading the opening chapters of a story that concludes billions of years later with those serene, ancient spheres of stars. They are a lasting gift from the chaos of creation, cosmic diamonds forged under immense pressure and scattered into the halos of galaxies to shine for eons. While the gravitational drama unfolds and new stars ignite, there is another, more subtle exchange taking place within the chaos, a silent trade of the very elements that compose worlds and life itself. When galaxies collide, they do not simply pass through one another like ghosts. They mingle, they share, and they forever alter each other's chemical identity. This intricate exchange of gas and metals is a hidden current flowing through the cosmic embrace, a process that seeds the universe with diversity and complexity. Imagine the vast clouds of interstellar gas within each galaxy as unique recipes. One galaxy might be relatively pristine, its gas dominated by the primordial hydrogen and helium from the Big Bang, with only a faint sprinkling of heavier elements forged in earlier generations of stars. Its partner, however, might be a well-stocked kitchen, its gas enriched with copious amounts of carbon, oxygen, iron, and nitrogen from a long and vigorous history of star formation and death. As these two galaxies merge, their gas clouds don't just collide, they interpenetrate and violently stir together. Powerful shock waves from the impact act like a cosmic whisk, churning these different mixtures into a new, homogenized blend. This isn't a gentle mixing. It's a turbulent, chaotic process that can spread enriched material from one galaxy to another, effectively polluting the pristine partner with the building blocks of planets and life. The consequences of this cosmic alchemy are profound and can explain some of the most puzzling observations astronomers make. We sometimes find galaxies that, by all rights, should be too young or too isolated to have such a high abundance of heavy elements or metallicity. Their high metal content is an anomaly, a clue pointing to a past interaction where they received a massive infusion of enriched material from a more evolved companion. Conversely, we might see a galaxy that appears to have gas moving in the wrong direction, or with unexpected speed, a kinematic signature that betrays the gravitational pull of a recent visitor that left behind a gift of foreign gas. This exchange can even create strange, hybrid regions within a galaxy where the chemical composition is completely out of sync with the surrounding stars, a lingering ghost of a past merger. Mapping these complex flows is one of the great challenges of modern astrophysics. The material doesn't move in simple, predictable streams. Simulations reveal an incredible complexity. Some gas loses its momentum and falls directly toward the galactic center, feeding the supermassive black hole or igniting a central starburst. Other streams are flung outward into the vast galactic halo, forming a reservoir of hot, enriched plasma that might one day cool and rain back down onto the galaxy. And a significant fraction can achieve escape velocity, blown entirely out of the system by powerful galactic winds to become part of the intergalactic medium, enriching the void itself. To trace these paths, astronomers must become cosmic detectives following elemental clues. They use the light from distant quasars as a flashlight. As this light passes through the halos of intervening galaxies, specific elements in the gas, like oxygen, silicon, or carbon, imprint their unique absorption fingerprints on the quasar spectrum. By decoding these absorption lines, we can identify the composition, temperature, and velocity of the gas, slowly piecing together the story of its origin and journey. This grand cycle of redistribution is fundamental to the story of our own existence. The atoms that make up our planet and our bodies were forged in the hearts of stars that died long before our sun was born. Their explosive deaths scattered these elements into the interstellar medium, and it is highly likely that a gravitational shock wave from an ancient galactic encounter helped compress that enriched cloud, triggering the collapse that led to our solar system. We are not just children of the stars, we are the beneficiaries of an immense cosmic recycling program, where the violent embraces of galaxies serve as the great mixers, stirring the pot of creation and ensuring that the ingredients for new stars, new planets, and potentially new life are spread far and wide. This secret trade between galaxies is what builds a universe rich with possibility, connecting the fate of distant island universes to the very chemistry of our own world. And as if the brilliant starbursts and gravitational chaos weren't enough, these cosmic collisions unleash yet another incredible force, a tempest that can blow clear through a galaxy and out into the void beyond. Picture the aftermath of those furious waves of star formation, not just the birth of new suns, but also their spectacular, explosive deaths. When massive stars reach the end of their short lives, they don't fade quietly. They detonate as supernovae, and in the crowded, violent environment of a merging galaxy, these explosions happen in rapid succession, like a string of cosmic firecrackers. Each one sends a powerful shockwave racing through the surrounding gas, heating it to millions of degrees and pushing it outward, but the force doesn't stop there. The intense radiation from millions of young, hot stars also pours outward, exerting a steady pressure on the gas and dust, much like a strong wind pushing against a sail. In some cases, the awakened supermassive black hole at the galaxy's center adds its own tremendous energy to the mix, blasting out jets of material and radiation. All these forces combine into a single, overwhelming outflow, a galactic wind, a hurricane of superheated gas and cosmic rays that can rush out of the galaxy at speeds of thousands of kilometers per second. The shape and structure of these winds are as varied as the mergers that create them. In some systems, the outflow is surprisingly orderly, channeled by the galaxy's magnetic fields or its rotation into two powerful bipolar jets that shoot out from the poles above and below the galactic disk. These focused winds can travel astonishing distances, sometimes punching entirely through the galaxy's own halo and venting directly into intergalactic space. In other mergers where the chaos is more extreme and the gas distribution is less symmetrical, the wind is a chaotic, multipolar frenzy, blowing out in all directions like steam from a cracked kettle, with no clear direction or axis. The specific geometry of the collision plays a huge role in determining which pattern emerges. A direct head-on merger might stir the gas into a more chaotic frenzy, while a gentler, more gradual interaction could allow for a more structured, bipolar flow. This makes each galactic wind a unique fingerprint of the violence that created it. The impact of this great exhalation is nothing short of transformative for the galaxy and its surroundings. First and foremost, it acts as a powerful self-regulating mechanism. All that gas being blown away is the very fuel for future star formation. By ejecting it, the wind effectively starves the galaxy, quenching the furious starburst and putting a decisive end to the period of rapid creation. This is a key process in turning a gas-rich, star-forming spiral into a quiescent, red and dead elliptical galaxy. But the material doesn't just disappear. The wind carries with it a precious cargo of heavy elements: oxygen, carbon, iron, and more, freshly forged in the supernova and stellar furnaces. It injects this enriched material into the vast, sparse volume of space surrounding the galaxy, known as the circumgalactic medium. This region, once a relatively pristine void, becomes polluted with the building blocks of planets and life. This process is the primary way galaxies seed the intergalactic medium with metals, enriching the entire cosmic ecosystem for eons to come. In a very real sense, the rocky planets in distant solar systems and the chemistry of any life upon them owe their existence to these ancient galactic winds. Furthermore, these winds can even reach out and touch their neighbors. In a dense galaxy cluster, the powerful wind from one massive merger can sweep over nearby dwarf galaxies, either compressing their gas to trigger a wave of star formation or, conversely, stripping their gas away entirely and halting their evolution in its tracks. The wind becomes a messenger of the collision, carrying news of the violent event far beyond its source and influencing the fate of other galaxies in the neighborhood. Unraveling the full complexity of these winds requires astronomers to use every tool at their disposal. They observe them in X-rays to see the hottest gas, in radio waves to trace the cooler material, and in visible light to see the glowing filaments where the wind shocks against the intergalactic medium. They then feed this data into immensely complex computer simulations that try to model the physics from the small-scale explosions of individual supernovae all the way up to the large-scale flow of the wind across hundreds of thousands of light-years. It is a daunting challenge, but one that is crucial for understanding the full life cycle of galaxies. These great winds are the breath of galaxies, a final, powerful exhale following the intense exertion of their violent embrace, forever altering their own destiny and the chemistry of the cosmos around them. Now, let's journey into the very heart of the chaos, to the dense, dynamic cores where the most dramatic transformations of a galactic merger unfold. The central region of a galaxy is its bustling downtown, a place of immense density and activity, and when two galaxies collide, this downtown district is completely and utterly rewired. The forces at play here are immense, pulling matter inward, reshaping stellar orbits, and triggering explosive events that can define the galaxy's future for billions of years. The evolution of these galactic centers is a complex ballet of physics, a mystery where gravity, gas dynamics, and sheer violence combine to write a new chapter in the life of a galaxy. The first and perhaps most significant change is a massive inflow of gas. Remember those shock waves from colliding gas clouds that trigger starbursts throughout the disks. Those same forces also act to rob the gas of its angular momentum, its orbital energy. It's like applying a universal brake, causing vast rivers of cold gas to lose their speed and begin a long, inevitable spiral down toward the gravitational well at the center. This incoming flood of fuel has two immediate and dramatic consequences. First, it can ignite a furious burst of star formation right in the galactic nucleus, creating an incredibly dense and brilliant central star cluster. Second, and even more profound, it provides a feast for the supermassive black hole that almost certainly resides there. This influx of material is what can awaken a dormant black hole, turning it into an active galactic nucleus and unleashing energies that can outshine the entire galaxy. As this is happening, another, more subtle process is rearranging the very structure of the central stars. This is due to a phenomenon called dynamical friction. Imagine the two supermassive black holes from each galaxy, along with their entourages of stars, sinking toward the new common center of the merged galaxy. As they move through the dense background of stars, their immense gravity pulls on these stars, creating a wake behind them, much like a boat moving through water. This wake exerts a gravitational drag on the moving object, slowly but surely sapping its orbital energy. This friction causes the black holes and the most massive star clusters to sink inward fastest, while also causing the orbits of countless other stars to circularize and randomize. It's this process that helps to build up the characteristic smooth, featureless bulge that defines an elliptical galaxy, erasing the ordered structure of the former spiral disks. The outcomes of this central transformation are as varied as the mergers themselves. In some cases, a merger might completely destroy a pre-existing, tightly bound nuclear star cluster, scattering its stars into the new, larger bulge. In other cases, the intense inflow of gas might actually birth an entirely new nuclear cluster, more massive and brilliant than before. Often, the result is the buildup of a classic central bulge, a vast, rounded collection of older stars. But sometimes, particularly in less violent mergers or those with specific geometry, the result is a pseudobulge, Unlike a classical bulge with its random stellar orbits, a pseudobulge often retains some of the ordered rotation of the original disk and can even show signs of ongoing star formation, looking more like a bright central mini-spiral within the larger galaxy. Observations of merging galaxies often reveal surprising clues about their violent pasts right in their cores. We sometimes see galaxies with double nuclei, two bright, distinct centers lingering long after the main bodies of the galaxies have merged. This is the telltale sign of two supermassive black holes still in the process of inspiraling, or perhaps stalled at that infamous final Parsec separation. Even more intriguing are discoveries of offset active galactic nuclei, where the brilliant energy source of a feeding black hole is not precisely at the galaxy's photometric center. This could be the signature of a recent merger where the black holes haven't yet settled, or it could be evidence of a powerful gravitational wave recoil kick from a past black hole merger that literally sent the monster flying from the very center, leaving a displaced engine of incredible power. Understanding the intricate evolution of these galactic centers is absolutely crucial because it is the linchpin that connects the large-scale collision to the ultimate fate of the galaxy. The activity here decides whether the galaxy will become a quiescent red elliptical or a star-forming blue spiral. It determines the growth history of the supermassive black hole and the feedback it exerts on its host. The heart of a galaxy is its control center, and a merger is the most dramatic corporate takeover imaginable, one that completely overhauls management and sets a new policy for the eons to come. By learning to read the subtle signs in the light and motion of these central regions, we are reading the most intimate pages of a galaxy's autobiography, written in the aftermath of a truly cosmic embrace. While the chance of two stars actually colliding is almost zero, the true danger to a planetary system during a galactic merger is not impact, but the immense gravitational chaos that follows. The stable, predictable orbit of a star around its galactic center, a path that might have been constant for billions of years, is suddenly thrown into a turbulent sea of shifting gravitational forces. A star and its planetary entourage could be flung onto a wildly eccentric new path, one that plunges it dangerously close to the bustling, radiation-filled galactic core. Even more terrifyingly, a strong enough gravitational kick could eject an entire solar system entirely, hurling it out into the freezing, dark emptiness of intergalactic space, its planets forever cut off from the light and warmth of any other star, destined for a slow, deep freeze into eternal night. Beyond the gravitational upheaval, there is the threat of radiation. The same starbursts that paint merging galaxies with beautiful blue hues of newborn stars are also factories for death. Massive stars live fast and die young, exploding as supernovae at a vastly increased rate. For a planetary system passing even remotely near one of these regions, the consequences could be catastrophic. A nearby supernova, or even a dense cluster of them, could bathe a planet in a lethal wave of X-rays and ultraviolet radiation, effectively sterilizing a once habitable world by stripping its atmosphere and scorching its surface. The very cosmic events that create the elements for life also possess the power to utterly erase it. Yet, for all this destructive potential, these same violent processes might also be incredible engines of creation and enrichment. While one world is being sterilized, another might be receiving the very gift it needs to spark life. The supernova that unleash deadly radiation also forge and spread heavy elements like carbon, oxygen, nitrogen, and phosphorus, the fundamental building blocks of planets and life itself. A planetary system that forms from gas enriched by a past merger might be far more likely to develop rocky, terrestrial worlds with the right chemistry for complexity. It's a profound cosmic paradox, The same event that can destroy a world might provide the essential ingredients for life to arise on another. This creates a complex and fascinating balance that makes the net effect on galactic habitability one of the great unanswered questions in astrobiology. Does the gravitational disruption and increased radiation of a merger decrease the number of habitable worlds? Or does the chemical enrichment and the triggering of new star formation actually increase it? The answer is likely not a simple yes or no, but a nuanced tapestry that depends on a planet's specific location within the galaxy during the collision, the timing of the merger, and even the type of life we're considering. Perhaps simple, hardy microbial life could survive the temporary increase in radiation, while more complex organisms could not. This forces us to expand our view in the search for life beyond Earth. We must consider not just a planet's immediate environment around its star, but the entire history of its galaxy. The most life-friendly corner of the cosmos might not be a quiet, unchanging spiral arm, but a region that experienced a carefully timed merger, one that provided the enrichment for life without the gravitational violence to tear it all apart. The secret history of our own solar system's elements suggests we may all be children of such a violent and creative cosmic past. But how do we even know our own galaxy has such a violent past if the evidence can fade over billions of years? This is the core of a fascinating cosmic detective story, the search for galactic merger remnants. The challenge is that not every collision leaves behind the spectacular tidal tails and brilliant starbursts we see in the Antennae galaxies. Some mergers are so ancient that the visible structures have long since dissipated. Their stars settled into a new, seemingly peaceful equilibrium. Others were so gentle or involved such a small companion that the disturbances were minimal from the start. Uncovering these hidden histories requires astronomers to become forensic scientists, looking for subtle clues that betray a past of cosmic violence. The first and perhaps most powerful clue lies in the motions of the stars themselves. In a galaxy that has lived a quiet, isolated life, the stars in its halo, the vast spherical cloud that surrounds the main disk, should orbit in a relatively random but predictable pattern. But if that halo was built up by cannibalizing smaller galaxies, the stars from those victims will often retain the memory of their original motion. They move together in great streams and clouds on orbits that are distinct from the native population. This is like noticing a group of people in a crowd all walking in the same direction and at the same speed. It suggests they arrived together from somewhere else. By using powerful telescopes like Gaia, which maps the positions and motions of billions of stars with incredible precision, astronomers can trace these ghostly rivers of stars, the skeletal remains of long-dead dwarf galaxies as they wrap around our Milky Way. Another telltale signature is chemical. Stars that form together in the same cloud of gas will have a nearly identical chemical composition, a specific fingerprint of elements that is unique to that natal cloud. Stars from a different galaxy, which formed from gas with a different enrichment history, will have a different chemical fingerprint. So, even if the stars from a merged galaxy have been completely scattered throughout the halo, astronomers can still identify them as a family by their shared chemistry. By analyzing the light from these stars with spectroscopy, they can find groups that are chemically distinct from the majority, pinpointing them as immigrants from another system. This is how we identified the Gaia Enceladus galaxy, a dwarf galaxy that collided with the Milky Way billions of years ago. Its stars are both kinematically linked and chemically similar to each other, but different from the stars around them. Sometimes the evidence is even more subtle. In the very central regions of a galaxy, a major merger can create a population of stars with unusual orbits or a distinct age. Some galaxies have counter-rotating stars, where one group of stars orbits in the opposite direction to the rest, a clear sign of a past acquisition. Others might have a faint underlying structure, a slight asymmetry, a barely detectable ripple in the distribution of starlight that can only be revealed by subtracting a computer model of a perfect, undisturbed galaxy from the actual image. These faint shells or plumes are the galactic equivalent of an archaeological tell, a mound built up by layers of ancient settlements. The ultimate goal of this detective work is galactic archaeology, reconstructing the entire assembly history of a galaxy by studying the fossils it contains. For our own Milky Way, each stellar stream and chemically distinct group is a chapter in its autobiography. The challenge is that later mergers can overwrite the evidence of earlier ones, and the faintest signals are incredibly difficult to detect against the bright backdrop of billions of stars. Developing new, more sensitive ways to find and date these remnants is crucial. It allows us to move beyond simply knowing that mergers happen, to understanding how many have occurred, how long ago they happened, and what kind of galaxies were involved. This, in turn, helps us test our models of galaxy evolution against the one galaxy where we can study the evidence in the most exquisite detail, piecing together the story of how our cosmic home was built, one violent embrace at a time. But while we often picture these cosmic collisions in terms of brilliant starbursts and dramatic structural changes, some of the most profound transformations are far more subtle, hidden in the very spin and motion of the stars themselves. The rotation of a galaxy is its fundamental heartbeat, a rhythm set billions of years ago, and a galactic embrace can completely rewrite that rhythm. For a majestic spiral like our Milky Way, this rotation is everything. It's the force that gives the galaxy its iconic flattened disk and its graceful, winding arms. The stars orbit in a grand, orderly fashion, a synchronized dance around a common center. But when another galaxy enters the picture, this harmony is thrown into chaos. The gravitational forces at play during a merger act like a cosmic hand reaching into the clockwork, scrambling the gears and fundamentally altering its tick. The outcome of this gravitational intervention depends almost entirely on the scale of the encounter. In a major merger between two spirals of similar size, the result is often a complete demolition of ordered rotation. The gravitational tug of war is so violent and chaotic that it randomizes the orbits of the stars, stripping them of their shared directional motion. Instead of circling in a neat disk, the stars are thrown into a jumbled, three-dimensional swarm where their movements are supported by random pressure, much like a buzzing cloud of bees. This is the fundamental transformation that turns two spinning spirals into a single, slowly rotating elliptical galaxy. The original spin isn't just slowed down, it's effectively converted into a different form of energy, the random motion of the stars. It's a cosmic act of dissipation where the graceful spin of a disk is traded for the hot, disordered motion of a sphere. However, not all collisions are so destructive. A minor merger where a large spiral galaxy consumes a much smaller dwarf companion can have a very different effect. Instead of destroying the disk, the smaller galaxy's gravity can impart a new and complex pattern onto it. As the dwarf galaxy is torn apart by tidal forces, its stars are strewn along its orbital path, often creating a faint warp in the larger galaxy's disk, a gentle bending like a vinyl record left in the sun. In some cases, this interaction can actually transfer angular momentum, potentially even speeding up the rotation of the outer disk or triggering the formation of a new set of spiral arms. The key player in these more subtle interactions is often the dark matter halo. The extended, invisible halo of the smaller galaxy can, as it passes through the larger one, exert a gravitational torque that twists the disk, leaving a lasting imprint on its rotational pattern long after the visible stars of the dwarf have been assimilated. The true complexity of this process is revealed when we look at the most extreme examples, galaxies with counter-rotating components. Imagine a galaxy where the stars in the inner region orbit clockwise, while a vast ring of gas and stars in the outer halo orbits counterclockwise. This bizarre configuration is almost always the signature of a past merger, where a galaxy has captured material that was orbiting in the opposite direction. This acquired material retains its original angular momentum, creating a celestial traffic jam of epic proportions with two flows moving in opposite directions. Such a system is a frozen record of a specific type of encounter, telling us not only that a merger happened but also the angle and direction from which the victim galaxy arrived. To decode these stories of spin, astronomers rely on incredibly powerful tools known as integral field spectrographs. Instruments like the Very Large Telescope's MUSE or the Hubble Space Telescope's STIES don't just take a picture of a galaxy, they take its fingerprint. They dissect the light from every single point in the galaxy, allowing scientists to map the velocity of the stars and gas across its entire structure. The result is a detailed velocity map, a colorful diagram where red might indicate material moving away from us and blue indicates material moving toward us. In a normal spiral, this map shows a smooth gradient, a clear signature of orderly rotation. But in a merging system, the map becomes a chaotic splatter of colors, with swirls, knots, and opposing flows that reveal the immense gravitational turmoil reshaping the galaxy's motion. By comparing these intricate observational maps with sophisticated computer simulations, we can rewind the cosmic tape and determine the precise orbital parameters of the collision. The angle, the speed, the mass ratio that led to the rotational state we see today. Understanding the impact on rotation is about more than just cataloging different types of motion. It's about connecting a galaxy's present state to its entire history. The spin of a galaxy is a silent witness, a conserved property that can be transferred, transformed, or reversed, but never erased. By learning to read these rotational signatures, we gain the ability to look at a seemingly placid elliptical galaxy and know that it was once two vibrant spirals, their orderly dance forever lost to a moment of ancient violence. Or we can look at a warped disk and see the ghost of a long-digested dwarf galaxy, its final passage still etched in the subtle twist of its host. It is a reminder that in the cosmos, even the most fundamental motions tell a story, and every rotation holds a secret. Now, as we've seen, these cosmic collisions unleash incredible forces of creation and destruction, but what ultimately decides the final fate of the merged galaxy? It all comes down to a delicate and powerful cosmic balancing act known as feedback. Imagine a galaxy during a merger as a complex engine, with two powerful systems vying for control. On one side, you have the furious starbursts, where massive stars are born and die in supernova explosions, pouring energy back into their surroundings. On the other, you have the active galactic nucleus, the supermassive black hole at the center, which can unleash jets and radiation of unbelievable power. These are the two primary sources of feedback, and they act as the universe's own regulatory mechanisms, a system of checks and balances that either accelerates or halts the galaxy's evolution. This feedback can operate in two seemingly opposite ways, and which one dominates is one of the great unresolved puzzles. First, there's negative feedback. This is the universe's brake pedal. The intense radiation and powerful winds from all those new stars, combined with the potential outburst from the central black hole, can heat up the surrounding gas to such extreme temperatures that it can no longer collapse to form new stars. Think of it like a strong wind blowing on a pile of leaves you're trying to gather. It scatters the material, preventing you from building anything. In some cases, this feedback is so powerful it can drive a galactic wind that blows a significant portion of the galaxy's gas supply clear out into intergalactic space. This process effectively quenches the galaxy, starving it of fuel and leading it down the path to becoming a quiet, red and dead elliptical galaxy, its star-forming days over for good. But then there's the other side of the coin, a positive feedback. This is the accelerator. It might seem counterintuitive, but the very same forces can sometimes trigger more star formation instead of suppressing it. The shockwaves from supernova explosions or the outer edges of powerful AGN jets can slam into nearby, relatively calm clouds of gas. Rather than just heating and dispersing them, these shocks can compress them, squeezing them to the critical density needed for gravitational collapse. It's like rolling a snowball. You apply pressure to loose snow, and it packs together into a solid, growing ball. In this scenario, the feedback doesn't shut down the factory. It makes it more efficient, creating a self-perpetuating cycle where star formation begets more star formation, potentially turning the galaxy into a veritable star-forming monster for a relatively brief, explosive period. The ultimate outcome of a merger, whether it becomes a quiescent giant or a brilliant starburst, hinges on the precise and poorly understood balance between these two opposing feedback loops. This balance isn't fixed. It's a delicate dance that depends on a huge number of factors. The mass of the galaxies involved plays a crucial role. A merger of two giants might channel so much gas to the center that it triggers an AGN powerful enough to quickly shut everything down. The environment matters too. A galaxy in a dense cluster might have its gas stripped away by external forces, limiting the raw material available for feedback to act upon. Even the specific geometry of the collision influences how and where the feedback energy is deposited, making every merger a unique cosmic experiment. Unraveling this mystery is one of the most daunting challenges in all of modern astrophysics. It requires scientists to build computer models that can simultaneously account for the immense scale of galactic dynamics and the tiny scale physics of how individual photons of light interact with gas particles. They have to model the propagation of radiation, the hydrodynamics of turbulent winds, the influence of magnetic fields, and the energy output from millions of supernovae, all interacting across light years of space. It's a multi-scale problem of almost unimaginable complexity. These feedback loops are the hidden conductors of the cosmic orchestra, silently directing the movements of gas and stars, determining the final movement of the galactic symphony. Their secrets are the final piece of the puzzle, the key to understanding why the universe produces such a beautiful and diverse array of galactic forms from the same basic laws of physics. Furthermore, the grand tapestry of the cosmos itself, the very architecture of the universe on its largest scales, dictates the rhythm and style of these galactic dances. It's a profound realization that galaxy collisions are not random, isolated accidents. Instead, they are choreographed events, their frequency and ferocity determined by a galaxy's address within the immense cosmic web. This vast structure, built from dark matter and traced by the glitter of galaxies, resembles a colossal network of interconnected filaments and nodes, with immense, empty voids stretching between them. Where a galaxy resides on this web, whether in a dense urban cluster, a bustling galactic group, or an isolated rural void, profoundly shapes its social life and its likelihood of a dramatic gravitational embrace. The most dramatic collisions occur in the universe's dense metropolitan centers, massive galaxy clusters. These are gravitational beehives, swarming with thousands of galaxies all buzzing around a common center at incredible speeds. In this chaotic environment, close encounters are a regular fact of life. But here, the high relative speeds of the galaxies often prevent a slow, merging waltz. Instead, they experience rapid, repeated gravitational flybys, a process astronomers call harassment. These high-speed interactions can puff up galactic disks, trigger bursts of star formation, and slowly strip away a galaxy's outer layers of stars and gas over billions of years. However, the true giants of these clusters, the brightest cluster galaxies, grow through a more brutal form of consumption known as galactic cannibalism. Located at the very heart of the cluster's gravitational well, these behemoths use their immense gravity to slowly devour smaller galaxies that venture too close, growing to monstrous sizes by absorbing their neighbors in a series of minor mergers. It's a process of steady accretion rather than a single, violent collision. In stark contrast, the cosmic countryside, the vast, empty voids that make up most of the universe's volume, is a place of profound isolation. Here, galaxies are few and far between, separated by immense gulfs of empty space. Collisions in these regions are exceptionally rare events, separated by many billions of years. When they do occur, they are likely to be very different from their cluster counterparts. The galaxies involved are often more gas-rich, having avoided the stripping effects of a dense environment, and their slower relative motions allow for a more gradual, complete merger. A collision in a void might be a slow, stately, and thorough union, a private event unfolding over eons with none of the chaotic interference seen in a crowded cluster. But the large-scale environment's influence begins long before any actual collision. It preps the galaxies for their eventual encounter. A spiral galaxy living in a dense cluster may have already had much of its life-giving gas stripped away by the searing heat of the intracluster medium or by ram pressure as it moves through this hot soup. By the time it experiences a close encounter, it is already gas-poor or red and dead, leading to a dry merger that produces little new star formation. Meanwhile, a similar spiral in a group or void likely retains its full reservoir of gas, setting the stage for a wet merger full of the brilliant starbursts and chaotic transformation we often associate with these events. The environment doesn't just arrange the dance, it also chooses the costumes and the music. Unraveling this intricate connection requires a level of cosmic cartography on an almost unimaginable scale. Astronomers must conduct enormous surveys of the sky, painstakingly mapping the three-dimensional positions and motions of millions of galaxies to accurately reconstruct the architecture of the cosmic web. Only by understanding this grand design can they then hope to comprehend the small-scale drama of individual collisions. This mystery beautifully ties the fate of a single galaxy directly to the largest structures in existence. It reveals that the story of a galactic embrace is not just a local tale of two partners, but a single sentence in a story written across the entire universe. A secret history inscribed into the very fabric of the cosmos itself. Yet for all the grand forces shaping these cosmic encounters, from dark matter's pull to the fury of starbursts, there is an invisible dimension that governs every aspect of the process, one that remains profoundly challenging to grasp: the dimension of time itself. We speak of galaxy collisions unfolding over hundreds of millions or even billions of years, but these numbers are so vast they defy human comprehension. To put it in perspective, the entire history of our species, from the first steps of Homo sapiens to our modern civilizations, spans a mere 300,000 years. A single galactic merger could take 100 times longer than that from its first gravitational whisper to its final, settled silence. This immense timescale presents perhaps the most fundamental challenge in astronomy. We are granted only a single, frozen snapshot in a billion-year-long movie. We must learn to reconstruct the entire epic narrative from a single frame. The dance of merging galaxies follows a sequence of distinct stages, each with its own telltale signature, if only we know how to read it. It begins with the first approach, a slow, gravitational courtship where two galaxies, drawn together by their mutual pull, start to feel each other's influence across millions of light years. At this earliest stage, the signs are subtle, perhaps a slight warping of one galaxy's disk, a minor asymmetry in its spiral arms, a faint bridge of hydrogen gas beginning to stretch between them. The next major act is the first close passage, where the galaxies swing by each other, their gravity now working like a colossal tidal force. This is when the most dramatic and beautiful features are born. The long, graceful tidal tails of stars and gas are pulled out, stretching for hundreds of thousands of light years, creating those iconic celestial structures that signal a merger in progress. Following this, the galaxies, now locked in a gravitational embrace, may swing apart again on long, looping orbits, only to be pulled back together for subsequent passages, each one drawing them closer, further distorting their shapes and mixing their material more violently. The final act is the complete merger, the slow, inevitable coalescence of their cores into a single new galaxy, often accompanied by a final, furious burst of activity as their supermassive black holes finally spiral inwards and merge. Our ability to pinpoint exactly where a galaxy pair is in this sequence is a complex detective game. Astronomers use a toolbox of techniques to estimate the timing. They can analyze the ages of the stellar populations within the tidal tails and starburst regions. By measuring the color and brightness of the stars, they can determine if a cluster is, say, 50 million years old or 500 million years old, providing a rough clock for when that particular feature was created. They can also create incredibly detailed computer simulations, running thousands of virtual collisions with slightly different starting conditions, angles, speeds, masses, until they find a model that produces a system that looks exactly like the one we observe through our telescopes. The simulation then acts as a cosmic time machine, showing us the most likely past and future of the real-life collision. However, these methods are filled with uncertainty. For very ancient mergers, where the visible signs like tidal tails have long since faded and the stars have settled into a smooth equilibrium, dating the event becomes extraordinarily difficult. It's like trying to determine the exact date of a prehistoric battle by examining the erosion patterns on a stone arrowhead found in a field. The evidence is there, but it's faint and blurred by eons of subsequent history. The stellar populations become more mixed, their ages harder to distinguish, and the dynamical memory of the collision fades as the galaxy relaxes. This is why the impending merger between our Milky Way and the Andromeda Galaxy is so valuable. It is a future event that we can model with much greater confidence, giving us a nearby template to understand the precise timing of stages in other, more distant systems. Understanding these timescales is not an academic exercise. It is the crucial link that connects cause and effect in the story of galactic evolution. Knowing whether the starburst in a particular galaxy happened 50 million years ago or 500 million years ago changes our entire understanding of its current state. It tells us if we are seeing a system that is still reeling from the initial impact or one that is well on its way to recovery. This temporal context is what allows us to truly test our simulations against reality. A model that produces a galaxy that looks right but does so on the wrong timescale is a model that is missing a key piece of physics. The patient, slow-motion dance of galaxies forces us to adopt a cosmic perspective on time, a humbling reminder that the universe operates on a schedule so grand that our own fleeting existence is but a momentary spark in the encompassing darkness. Among the countless galactic structures born from cosmic violence, few are as visually striking and enigmatic as the polar ring galaxy. Picture a classic, old elliptical galaxy or a lenticular system, a relatively flat, featureless disk of stars. Now imagine encircling this central hub with a brilliant, narrow ring of gas, dust, and young blue stars, but with one incredible twist. This ring does not lie in the same plane as the galaxy. Instead, it orbits at a near-perpendicular 90-degree angle, spinning around the galaxy's poles like a belt around its waist. This is not a trick of perspective. It is a real, stable configuration that represents one of the most peculiar and informative outcomes of a galactic collision. The prevailing theory for the creation of these celestial marvels involves a very specific and delicate type of galactic encounter. The story likely begins with a larger primary galaxy, often a lenticular or elliptical type, which has a well-established rotating disk. Then, a smaller, gas-rich dwarf galaxy ventures too close on a trajectory that is almost perfectly perpendicular to the larger galaxy's plane. As the dwarf galaxy is torn apart by the immense tidal forces of its massive neighbor, its stars and dark matter may be scattered and assimilated. But its most precious cargo, its vast clouds of cold gas, can be captured by the larger galaxy's gravity. However, this gas isn't simply absorbed into the existing disk. Because it arrived on a perpendicular path, it retains much of its original angular momentum, settling into a new, stable orbit that circles the poles of the central galaxy. Over time, this captured gas reservoir can collapse, fragment, and ignite with the brilliant blue fire of new star formation, painting the polar ring we observe today. The very existence of these rings is a powerful testament to the enduring nature of angular momentum in the cosmos. For this delicate structure to persist for billions of years, as many of them have, the system must be incredibly stable. This presents a fascinating mystery for astronomers. What are the exact conditions that allow this stability? The ring must be in a nearly perfect equilibrium, with the gravitational pull of the central galaxy's bulge and the centrifugal force of the ring's rotation exquisitely balanced. Any significant misalignment or instability would cause the ring to precess, wobble, and eventually dissipate, either falling into the main disk or dispersing entirely. The fact that we see these rings at all suggests that the initial collision was a remarkably precise event, a cosmic billiard shot of just the right angle and speed to create a lasting gravitational sculpture. One of the most famous and well-studied examples of this phenomenon is the galaxy known as NGC 4650A, often simply called the Polar Ring Galaxy. Through powerful telescopes, it appears as a stunning, perfect example of the form. A bright, central core of older, yellowish stars is encircled by a beautiful, blue and dusty ring that is clearly tilted relative to the main body. This ring is not a static band of light. It is a vibrant, active stellar nursery. Spectroscopic observations confirm that the ring is vigorously forming new stars, its gas compressing and collapsing to create brilliant clusters that light up the structure. This active star formation is a key clue, telling us that the ring is a relatively recent addition in cosmic terms, likely less than a few billion years old, and that the gas within it is still dynamically settling into its new home. Studying these rare and beautiful systems provides astronomers with a unique laboratory for understanding fundamental physics. Because the ring orbits perpendicular to the main galaxy, it allows scientists to map the gravitational field of the central system in 3 dimensions. By measuring the velocity of the gas and stars in the ring at different points, they can trace the shape and distribution of the invisible dark matter halo that surrounds the galaxy. This is crucial because it helps test theories of how dark matter behaves, whether its halo is spherical, flattened, or perhaps even triaxial. The longevity of the ring itself also provides stringent tests for our models of angular momentum transfer during collisions and the dynamics of gas accretion. Each polar ring galaxy is a frozen moment in a complex gravitational dance, a natural experiment that occurred under perfectly tuned conditions, allowing us to peer deeper into the mechanics of how galaxies interact, evolve, and ultimately shape each other across the vast expanse of cosmic time. But for all the visible drama of colliding stars and swirling gas, the true architect of the merger remains hidden in the shadows, its presence only felt through the silent, persistent pull of gravity. We are talking, of course, about dark matter, the invisible scaffolding that makes up the overwhelming majority of a galaxy's mass. And just as the collision reshapes the luminous stars we can see, it also profoundly rearranges this dark, unseen component in ways that continue to mystify and challenge our understanding. The effect on dark matter distribution is a subtle but critical chapter in the story of any galactic embrace, one that leaves a lasting gravitational imprint on everything that follows. During a merger, the behavior of dark matter is utterly counterintuitive and completely different from that of normal matter. Picture 2 galaxies approaching one another. Their stars, while rarely colliding, are gravitationally pulled into those beautiful, long tidal tails. Their gas clouds slam together, creating shock waves and brilliant starbursts. But the dark matter halos that surround each galaxy, vast and diffuse spheres of this mysterious substance, behave like phantoms, because dark matter doesn't interact with itself or with normal matter through any force except gravity. These 2 halos can pass right through one another. There's no crashing, no friction, no violent interaction, just a ghostly interpenetration. They briefly merge into a single, more massive, and likely misshapen halo before, in some cases, separating again as the galaxies swing past each other. This strange passage, however, is not without consequence. The gravitational pull from these overlapping dark matter halos is the primary force guiding the entire merger. It acts as an invisible track, dictating the trajectories of the galactic cores as they swing around each other, and ultimately determining the final shape and structure of the merged galaxy. But the dark matter itself can be sculpted by the encounter. Computer simulations reveal that the halos can be stretched and distorted, developing asymmetries and offsets. In some cases, the dark matter can even be stripped away, forming its own faint, diffuse tidal streams that are completely invisible to telescopes, but whose gravitational influence can linger for billions of years. It's a cosmic rearrangement happening in a realm we cannot see, yet its effects are everywhere. The real challenge and the heart of the mystery is that we cannot observe this dark matter directly. We are forced to be cosmic detectives, using indirect clues to map its invisible presence. Our most powerful tool is a phenomenon known as gravitational lensing. The immense mass of a galaxy or cluster, dominated by its dark matter, warps the fabric of space-time around it. This warping acts like a lens, bending and distorting the light from more distant galaxies behind it. By meticulously studying the pattern of this distorted background light, astronomers can create a detailed map of the mass distribution in the foreground object, effectively tracing the outline of its dark matter halo. This allows us to see if the dark matter is offset from the visible stars, if it has been pulled into a different shape, or if it lags behind the galaxies after a collision. A stunning and definitive example of this is the Bullet Cluster, a system not of two galaxies but of two entire galaxy clusters that have collided. Observations provide a perfect separation of the components. The visible galaxies, largely unaffected by the collision, have mostly passed through one another. The hot, X-ray emitting gas from the two clusters, however, was slowed down by friction and now lags behind, sitting between the two groups of galaxies. But most importantly, the map of the total mass created through gravitational lensing shows that the vast majority of the mass, the dark matter, has continued on its path, perfectly aligned with the motion of the galaxies themselves. This provides breathtakingly direct evidence that dark matter is real, that it is separate from normal matter, and that it behaves exactly as predicted during a colossal impact. Understanding how dark matter is redistributed is not just an academic exercise. It is absolutely vital for testing the very models that define our understanding of the universe's composition. The way dark matter behaves in these extreme environments helps physicists distinguish between different theoretical candidates for what dark matter actually is. Does it behave as a cold, collisionless particle, as most models suggest? Or do our observations hint at something more complex, perhaps a slightly warm, dark matter, or even a self-interacting one? The precise details of how these halos merge, how they relax, and how they gravitationally influence the stars and gas long after the visible merger is over provide the crucial experimental data needed to answer these fundamental questions. The hidden hand of dark matter doesn't just guide the outcome of the collision. Its subtle movements during the event are our best window into understanding the true nature of this mysterious substance that shapes the cosmos. Amid the chaotic and often unpredictable outcomes of galactic collisions, where tidal tails stretch into infinity and stars are flung into disarray, there exists a phenomenon of breathtaking symmetry and precision: the ring galaxy. Picture a lone, brilliant circle of blue-white starlight, a perfect cosmic bull's-eye floating in the darkness. This is not a static structure or an illusion. It is a wave of creation, a propagating ring of star formation that expands outward from a central core like a ripple across a pond, one of the most strikingly beautiful and orderly structures to emerge from the violence of a galactic embrace. The most famous and archetypal example of this is the Cartwheel Galaxy, a celestial object so visually perfect it seems almost designed. Its appearance tells a clear story. Astronomers believe the sequence began with a large, undisturbed spiral galaxy, much like our own Milky Way going about its quiet business. Then, a smaller companion galaxy, perhaps a third of its size, committed the ultimate cosmic trespass. It didn't just swing past, it shot like a bullet directly through the center of the larger galaxy's disk. This precise, head-on collision is the key. The intruder itself would have passed through largely unscathed, but its gravitational influence acted as a stone dropped into the galactic pond. The force of this encounter sent a powerful density wave racing outward through the disk at supersonic speeds. This wave did not carry stars with it. Instead, it compressed the vast clouds of gas and dust that populated the disk. As this wall of pressure moved outward, it triggered the collapse of these clouds, igniting a firestorm of new star formation precisely at the wave's leading edge. What we see today is that expanding ring of brilliant, young, massive stars, a perfect circle of blue light that marks the current location of this stellar tsunami, while the galaxy's original core, older and yellower, sits slightly off-center, still reeling from the impact. However, the universe is rarely so simple, and the mystery of ring galaxies deepens when we look beyond this classic example. Not every ring galaxy has such an obvious culprit, a clear, nearby companion that can be pointed to as the instigator. This absence has led astronomers to consider alternative formation mechanisms. Perhaps some rings are born from a massive internal instability, a spontaneous gravitational collapse within the disk that creates a self-propagating wave without any external trigger. In other cases, the culprit might not be a full galaxy, but a massive, concentrated clump of dark matter passing through the disk, its immense but invisible gravitational pull creating the same compressive effect without a visible trace. There is also the possibility of accretion, where a large galaxy strips gas from a smaller, gas-rich neighbor. If this stolen material is funneled into the galactic disk with the right angular momentum, it could potentially splash down in a way that creates a ring-shaped wave. The variety of potential origins suggests that the ring structure might be a more common, albeit temporary, phase in a galaxy's life than we once thought, achievable through several different cosmic pathways. The life cycle of a ring galaxy is a race against time. The brilliant ring of young stars is a spectacular but fleeting phenomenon. Those massive blue stars are profligate with their fuel, burning out in only a few tens of millions of years and exploding as supernovae. These explosions inject tremendous energy back into the surrounding gas, heating it and potentially dispersing it, which can stifle further star formation and cause the ring to fade. The longevity of the structure depends on a delicate balance. If the galaxy has ample reserves of cold gas ahead of the wave, the ring can be sustained and even rejuvenated as it travels outward. But if the gas supply is sparse or is effectively blown away by stellar feedback, the ring will simply dissipate, leaving behind a more placid-looking galaxy with only a faint, ghostly echo of its once dramatic structure. This makes ring galaxies incredible natural laboratories, because the star formation is happening in a well-defined, coherent wave. Astronomers can study the entire life cycle of stars, from their birth in compressed gas clouds to their explosive deaths, all within a single, neatly packaged region, offering unparalleled insights into the physics of triggered star formation. Ultimately, the existence of these near-perfect rings is a testament to the universe's ability to create exquisite order from unimaginable chaos. They demonstrate that within the seemingly random violence of a galactic collision, the laws of physics can conspire to produce an outcome of stunning symmetry and beauty. The ring galaxy is a temporary monument, a celestial snapshot of a precise moment in a dynamic process, reminding us that even the most destructive cosmic events can leave behind a legacy of brilliant, structured creation. Imagine two galaxies on a collision course, each carrying a vastly different kind of fuel for the journey ahead. One is a gas-rich spiral, its reservoirs of cold hydrogen brimming with the raw potential for new stars. The other is a gas-poor elliptical, its stellar population aging quietly with little material left for renewal. When these two meet, their fate is not written solely by gravity, but by this fundamental difference in their initial conditions. The amount of cold, star-forming gas a galaxy possesses, its gas fraction, is perhaps the single most important factor in determining the entire narrative of a cosmic collision, from the brilliance of its starbursts to the very shape of the galaxy it leaves behind. This invisible ingredient dictates the violence and beauty of the resulting firestorm. In a merger between two gas-rich spirals, the outcome is a spectacle of creation. As their immense clouds of hydrogen and helium slam together, they create regions of incredible density, triggering a ferocious wave of star formation that can outshine the entire galaxy. This is a wet merger, and it's like throwing gasoline on a fire. The resulting galaxy is often a brilliant, messy, and sky remnant still teeming with activity and the potential for future stellar births. Conversely, when two gas-poor, red and dead ellipticals merge, it's a dry merger. with little gas left to compress and ignite. There is no spectacular starburst. The encounter is a relatively quiet, ghostly affair dominated by gravity alone, shuffling old stars into a new, larger, and even more featureless elliptical galaxy. It's the difference between a spectacular fireworks display and a silent, distant handshake. The plot thickens when we consider the activation of the central supermassive black hole. That incoming flood of gas from a wet merger doesn't just feed new stars, it's also a feast for the dormant monster at the galactic core. The chaotic inflows can funnel vast amounts of material directly toward the black hole, igniting it as a brilliant active galactic nucleus that can regulate the entire galaxy's future. In a dry merger, this simply doesn't happen. The black hole continues its slumber with no fresh fuel to awaken its incredible power. The gas fraction, therefore, acts as a master switch, controlling not only the birth of stars but also the awakening of the cosmic engine at the heart of the collision. Unraveling this mystery, however, forces astronomers to become cosmic detectives using indirect and challenging methods. We cannot simply point a telescope and see this cold gas directly in distant galaxies. Instead, we must listen for it. Cold hydrogen gas emits a faint radio whisper at a very specific wavelength of 21 centimeters. By using enormous radio telescopes, we can tune into this signal and map the gas content of nearby colliding galaxies. For more distant systems where this signal is too faint, we look for clues. We observe the faint glow of interstellar dust, which is intimately mixed with the gas, or we measure the rate of star formation and work backwards to estimate the reservoir of fuel that must be available to power it. Each method has its own uncertainties, piecing together a picture that is often frustratingly incomplete. The greatest unresolved puzzle in this story is a phenomenon known as star formation efficiency. Even in the most extreme, gas-rich mergers, only a small fraction of the available gas, often just a few percent, is actually converted into stars. The rest is heated, blown away by powerful galactic winds, or simply left behind. Why is this process so remarkably inefficient? What physical mechanisms prevent the galaxy from using all of its fuel? Is it the turbulent magnetic fields within the gas, the powerful feedback from newborn stars and supernovae, or the intense radiation from an active nucleus? This question strikes at the very heart of how galaxies evolve. It suggests that galaxies possess their own built-in regulatory systems, a series of cosmic breaks that prevent them from burning through their fuel too quickly, thus extending their star-forming lives and shaping their ultimate destinies. This profound reliance on initial conditions shatters the idea of galaxies as static islands of stars. Instead, we see them as dynamic entities with life cycles, their gas content representing their current age and vitality. A gas-rich galaxy is young at heart, still capable of dramatic change and vibrant creation. A gas-poor galaxy is in its later years, settled and stable, its major transformations behind it. When two galaxies embrace, they bring their entire histories with them in the form of this invisible fuel. The gas fraction is the key character that determines whether the collision will be a brief, fiery chapter or the concluding act that leads to a long, quiet retirement, forever shaping the legacy of the new galactic system born from the encounter. But as the grand merger fades and the brilliant starbursts dim, the legacy of the collision does not simply vanish. It settles, it endures, and it expands into the vast, dark reaches that surround the galaxy itself. We are talking about the galactic halo, that immense spherical cloud of ancient stars, globular clusters, and dark matter that envelops the bright disk of a galaxy like a faint cosmic fog. For a long time, these halos were thought to be quiet, pristine relics from the earliest days of the universe. but we now know they are something far more dynamic. They are the archives, the permanent records of every major encounter a galaxy has ever experienced. A galactic collision acts as a powerful engine for halo growth, violently stripping stars, gas, and even dark matter from the interacting galaxies and flinging them out into these distant orbits where they can persist for billions of years as a fossilized record of the violence. Our own Milky Way provides the most intimate and compelling evidence for this process. The Gaia Space Observatory has revolutionized our understanding of our galactic home by precisely mapping the positions and motions of over 1 billion stars. This incredible data has revealed that our halo is not a smooth, uniform cloud. Instead, it is a tangled web of stellar streams and clumps, the ghostly remains of smaller galaxies that were torn apart and consumed by the Milky Way's gravity. The most famous of these is the Gaia Enceladus galaxy, sometimes called the Gaia Sausage. This was a dwarf galaxy perhaps a quarter the size of the Milky Way that collided with and was devoured by our galaxy around 8 to 11 billion years ago. Its stars were not destroyed, they were shredded and scattered throughout our halo, where they still move together on similar, highly eccentric orbits. By identifying these stars through their distinct motions and chemical signatures, they are older and have a different metallicity than native Milky Way stars. We can literally piece together the story of this ancient, catastrophic merger that helped shape our galaxy's youth. This makes the galactic halo a treasure trove for cosmic archaeologists. Each stellar stream is a chapter in the galaxy's autobiography. The chemical composition of these stars acts as a clock and a birthplace certificate. Stars born together in the same dwarf galaxy will share a specific ratio of elements, more alpha elements like oxygen and magnesium if they formed early and quickly, or more iron if they formed later from gas enriched by many generations of supernova. By reading this chemical fingerprint, astronomers can not only identify which stars belong to which ancestral group, but also estimate when that group was absorbed. The kinematics, the precise motions of these stars, tell us about the angle and violence of the impact. It's a painstaking forensic process, sifting through the faint light of countless ancient suns to reconstruct events that occurred before our solar system even existed. However, reading this cosmic history book is an immense challenge. The signals are incredibly faint, and the story is layered and complex. Our halo is likely the product of dozens, if not hundreds, of separate accretion events, all overlapping and intermingling. Distinguishing the stream from one ancient merger from another requires enormous, sensitive surveys and incredibly sophisticated statistical models. It's like trying to listen to a single conversation in a crowded, noisy room where everyone is talking at once. New projects like the upcoming Vera-C, Rubin Observatory's legacy survey of space and time, are designed to do just that, map the entire sky with such depth and precision that it will reveal countless fainter streams and substructures, allowing us to build a far more complete family tree for our galaxy and others. Understanding the growth of these halos is about more than just tracing a single galaxy's past. It is a fundamental test of our entire model of the universe. The prevailing cosmological model, lambda cold dark matter, predicts that large galaxies like the Milky Way should have grown hierarchically by accreting and absorbing countless smaller building blocks over billions of years. The intricate structure we see in galactic halos with all its streams and shells is the direct observational proof that this process is real and ongoing. The number of streams, their masses, and their distribution precisely test the predictions of how dark matter behaves and how structure forms in the universe. The faint light of these ancient stars, once thought to be merely a backdrop, is actually the shimmering, enduring script of our galaxy's deepest history, a narrative of construction and destruction written across the darkness and waiting for us to finally learn how to read it. Amid the grand spectacle of colliding titans and brilliant starbursts, the universe also creates in whispers, crafting objects so subtle they nearly vanish against the inky blackness of space. These are the ultra-diffuse galaxies, and they represent one of the most enigmatic and counterintuitive products of cosmic interactions. Imagine a galaxy the size of our own Milky Way, but one that has been stretched and faded to an almost ghostly transparency. It contains a similar number of stars, but they are spread so thin that their collective light is nearly 1,000,000 times fainter, making these objects incredibly difficult to detect. They are the cosmic equivalent of a vast, faint watercolor wash on a dark canvas, and their very existence challenges our fundamental understanding of how galaxies assemble and evolve. The formation of these faint giants is a mystery with several compelling suspects, and galactic collisions are prime among them. One leading theory suggests they are born from the debris of a violent encounter. When two galaxies graze or merge, they can pull enormous tidal tails of stars, gas, and dark matter out into intergalactic space. Normally, gravity might cause this ejected material to collapse back in on itself, perhaps forming new dwarf galaxies or eventually falling back into the main merger remnant. But in some cases, the conditions might be just wrong enough for a different outcome. The tidal debris could be flung out with too much energy or angular momentum to efficiently coalesce. Instead of condensing into a compact, dense object, it remains as a vast, expanding cloud of stars that slowly settles into a stable but incredibly diffuse configuration, a lasting, ghostly monument to the violence that created it. This would make ultra-diffuse galaxies the celestial cousins of tidal dwarf galaxies, but ones that failed to achieve a denser form. Another pathway might involve a process less about creation and more about transformation. A smaller, normal dwarf galaxy could have a close encounter with a much larger one in a crowded cluster environment. This isn't a full merger, but a series of rapid, high-speed gravitational flybys known as harassment. Each pass strips away more and more of the dwarf's gas and loosely bound outer stars, puffing it up and stretching it out over billions of years. What was once a compact dwarf spiral is gradually transformed into a bloated, ultra-diffuse relic, its stars scattered across a much larger volume. This process is like pulling apart a ball of cotton candy, thinning it out until it becomes a wispy, extended veil. The galaxy isn't destroyed, it is fundamentally remade into a new, fainter form by the relentless gravitational tides of its environment. However, the plot thickens considerably when we consider their dark matter content, which varies wildly and adds another layer of profound mystery. Some ultra-diffuse galaxies, particularly those found floating in isolation, appear to be absolutely dominated by dark matter. Their stars move at surprisingly high velocities, suggesting they are embedded within massive, dense dark matter halos that provide the gravitational glue holding these faint systems together. These dark matter-rich galaxies are cosmic paradoxes, huge, massive objects that are almost completely invisible, acting as perfect natural laboratories for studying the properties of dark matter itself. Yet, in stark contrast, other ultra-diffuse galaxies found within the dense cores of galaxy clusters seem to have had nearly all their dark matter stripped away by repeated interactions, leaving behind a bare, wandering collection of stars with almost no invisible scaffolding. This dramatic difference tells us that there is no single origin story. The environment plays a crucial role in determining both their formation and their final nature. The discovery of these ghostly galaxies forces a major rethink of traditional galaxy formation theory. Our standard models, based primarily on the behavior of dark matter halos in the early universe, did not predict the existence of such large, faint objects in such abundance. Their presence tells us that the outcomes of galactic interactions are far more diverse and creative than we ever imagined. A collision doesn't just make bigger ellipticals or trigger starbursts. It can also leave behind these delicate, ephemeral structures that linger on the edge of visibility. They are a humbling reminder that for every brilliant, obvious result of a cosmic collision, there may be a dozen subtle, hidden consequences waiting to be discovered by the most sensitive telescopes and the most patient observers. These ultra-diffuse galaxies are the faint, lingering echoes of past encounters, challenging us to look deeper and see the universe not just for its most luminous giants, but for its quietest, most mysterious ghosts. Now consider one of the most fascinating and counterintuitive puzzles in the study of galactic collisions: the apparent synchronization of star formation across vast distances. We often imagine two galaxies as separate entities influencing each other from afar, but observations reveal something far more intimate. In many merging systems, the great bursts of star formation don't just happen randomly in each galaxy. They ignite in lockstep, as if an invisible conductor had given a downbeat, cueing a symphony of stellar birth simultaneously across millions of light years. This cosmic coordination suggests that the two galaxies are not just two partners dancing separately. They are acting as a single, interconnected system, responding to forces that bind them together in ways we are only beginning to comprehend. The classic example that showcases this phenomenon is a stunning pair known as the Mice galaxies, their long, slender tidal tails stretching out behind them like the tails of two swimming mice. Observations across multiple wavelengths tell a remarkable story. The rate of new star formation isn't just elevated in both galaxies, it rises and falls in near-perfect unison. This isn't a coincidence. It implies a form of communication, a physical mechanism that allows a change in one galaxy to directly and rapidly influence conditions in the other, despite the immense void separating them. The puzzle for astronomers is deciphering exactly how this message is sent and received across such a vast and empty stage. One compelling theory points to the role of immense shock waves racing through the shared medium between the galaxies. As the two systems swing past each other on their first close encounter, they don't move through a perfect vacuum. They are surrounded by and connected by a tenuous but pervasive halo of gas, their own circumgalactic medium. The gravitational violence of the encounter could send powerful pressure waves rippling through this shared gas. These shock waves would travel outwards at incredible speeds, compressing the gas clouds in both galaxies at roughly the same time. It would be like two drums placed far apart, both vibrating in sympathy when a single, powerful beat is struck on the stage between them. The shock wave acts as the drummer, providing a synchronized trigger for collapse and ignition. Another possibility involves a more subtle but equally profound gravitational connection. When two massive galaxies interact, they don't just orbit a fixed point, they reshape each other's gravitational potential, the very landscape of space-time that dictates how matter moves. The approach of one galaxy can dramatically alter the gravitational forces acting throughout its partner, even on the side farthest away. This global change in the gravitational field could simultaneously destabilize giant molecular clouds in both galaxies, causing them to collapse and form stars in a coordinated fashion. In this scenario, it's not a wave traveling through space, but an instantaneous change in the fundamental rules of the environment, affecting all the gas clouds at once, no matter which galaxy they call home. Unraveling this mystery is a task that pushes the limits of our computational power and theoretical models. It requires simulations of breathtaking complexity that can track not only the vast motions of stars and dark matter, but also the intricate physics of the gas, its chemistry, its thermodynamics, and how it responds to both radiation and shock fronts. Astronomers must create virtual pairs of galaxies and watch, in exquisite detail, to see if their models can naturally produce this observed synchronicity. If they can then rewind the simulation to identify the precise moment and mechanism that caused the star formation rates to align, providing a crucial key to understanding this cosmic coordination. This phenomenon fundamentally changes how we view these colossal encounters. It tells us that a galactic collision is not merely a gravitational interaction between two separate islands. It is the temporary formation of a new, single meta-system, a connected entity where events in one region have immediate and mirrored consequences in another. This deep interconnection is a powerful testament to the fact that even across the largest scales, the universe operates as a web of cause and effect, where no action is ever truly isolated, and the embrace of two galaxies can create a harmony that resonates through them both. And while the brilliant starbursts and gravitational chaos of a merger command our attention, a significant portion of the drama is unfolding not within the galaxies, but in the vast, seemingly empty space between them. The same colossal forces that compress gas to form new stars are also violently expelling it, launching vast rivers of superheated material out into the cosmic void. This ejected gas represents a critical, yet poorly understood, branch in the life cycle of a galaxy, a mass emigration of matter whose ultimate fate shapes the future of not just the merger remnant, but the entire intergalactic environment. When we witness the fiery brilliance of a starburst, we are seeing only part of the story. For every new star that ignites, the combined effect of countless supernova explosions and the intense radiation pressure from massive young stars creates a powerful, outward-moving front of energy. This energy acts like a cosmic broom, sweeping up surrounding gas and driving it out of the galaxy in a colossal outflow known as a galactic wind. In major mergers, these winds can achieve truly phenomenal scales, with material being ejected at speeds of thousands of kilometers per second, carrying with it a precious cargo of heavy elements: oxygen, carbon, iron, and silicon freshly forged in the stellar furnaces and supernova. This isn't a gentle leak, it's a systematic purging of the galaxy's star-forming fuel, a self-regulating mechanism that can eventually quench the very activity that created it. Once this material escapes the gravitational grasp of the galaxy, its journey becomes a cosmic mystery. The fate of this intergalactic gas is a story of three possible pathways, each with profound implications. The first possibility is a return. Some of this ejected material, particularly the denser clouds that were flung out with less velocity, may not achieve true escape velocity. Instead, it arcs high into the galaxy's extended halo, where it may eventually cool, condense, and fall back down onto the galactic disk in a process known as a galactic fountain. This returning rain of enriched gas could, billions of years later, provide the fuel for a new, more subdued era of star formation, seeding the next generation of stars with a richer abundance of metals. It's a form of cosmic recycling where the galaxy reuses its own expelled material. The second destiny is one of permanent exile. A large fraction of the gas, heated to millions of degrees and moving at tremendous speed, may indeed escape completely, becoming a permanent resident of the intergalactic medium. There it can form vast, tenuous clouds or long, filamentary structures that drift through the emptiness between galaxies. These clouds are incredibly difficult to detect directly due to their extremely low density, but they form a crucial component of the cosmic ecosystem. They act as a massive reservoir of normal matter, one that has been missing from our inventories of the universe's contents. Furthermore, by enriching this once pristine void with heavy elements, the galactic wind from ancient collisions has fundamentally altered the chemical composition of the entire universe. Any future galaxy that forms or any existing galaxy that passes through these enriched regions will inherit these building blocks of planets and life. The third and most fascinating possibility is the creation of something entirely new. In some cases, the ejected material, as it expands into space, might have just the right conditions for gravity to take over. Large clumps within the tidal tails or winds could collapse under their own weight, cooling and fragmenting to form new, gravitationally bound objects. These would be tidal dwarf galaxies, small galaxies born not from the primordial dark matter of the early universe, but from the recycled debris of a galactic collision. These second-generation galaxies would be intriguingly devoid of the significant dark matter halos that dominate their primordial cousins, making them unique laboratories for studying star formation and galaxy evolution under entirely different conditions. Tracking this incredible journey is one of observational astronomy's greatest challenges. The gas, once it leaves the bright confines of the galaxy, becomes incredibly diffuse and hot, emitting light mainly in the far ultraviolet and X-ray parts of the spectrum, which are largely absorbed by our own atmosphere. To map it, we must rely on space-based observatories like the Hubble Space Telescope and the Chandra X-ray Observatory, using them to study the faint, glowing filaments around nearby merging galaxies. Another powerful technique involves using the light of even more distant quasars as cosmic flashlights. As this brilliant light passes through the invisible clouds of intergalactic gas surrounding a merger remnant, specific elements in the gas, like oxygen and carbon, imprint their unique absorption fingerprints on the quasar's spectrum. By decoding these subtle absorption lines, astronomers can determine the composition, temperature, density, and velocity of the gas, slowly piecing together its origin story and ultimate destination. Understanding this grand expulsion is not just about cataloging where the gas goes. It is central to solving a major cosmological puzzle known as the missing baryon problem. Our best models of the Big Bang predict how much normal baryonic matter, the protons and neutrons that make up stars, planets, and us, should exist in the universe. Yet, when we add up all the matter we can see in galaxies, we find only about half of that predicted amount. The leading theory is that the other half is hiding in these very same vast, hot reservoirs of intergalactic gas, the WIM, or warm-hot intergalactic medium, which was largely seeded by outflows from galactic collisions and active nuclei over billions of years. The fate of intergalactic gas is therefore the key to finding the universe's missing matter, revealing that what was once thought to be empty space is in fact a dynamic and richly populated frontier, filled with the invisible, enriched breath of galaxies that have embraced. While the immense gravitational forces of a galactic collision are the undeniable architects of the grandest structures, the tidal tails, the starbursts, the merging black holes, there is a far more subtle, invisible force weaving through the chaos, one that we have only just begun to appreciate: magnetism. We've already touched on how these fields are stretched and amplified by the violence of a merger, but the truly fascinating mystery is whether they are merely passive passengers along for the ride, or if they actively seize the wheel, guiding the very progression of the collision itself. This idea of a two-way street, a dynamic conversation between gravity and magnetism, represents one of the newest and most complex frontiers in our understanding of these cosmic events. Imagine the vast clouds of gas within a galaxy as not just simple, formless blobs, but as intricate structures laced with invisible magnetic fields. These fields, though incredibly weak by earthly standards, act like a cosmic scaffolding, providing a subtle pressure that can resist the crushing force of gravity. In the tumultuous environment of a merger, this support can be decisive. Some of the most advanced computer simulations suggest that in certain conditions, strong, well-ordered magnetic fields can prevent a massive gas cloud from fragmenting into many smaller clumps. Instead of shattering into a multitude of average-sized stars, the cloud might be held together by its magnetic skeleton, collapsing into a single, monstrously massive star or an incredibly dense stellar nursery. This magnetic intervention would directly suppress the overall efficiency of star formation, putting a brake on the very process the collision is trying to accelerate. It's a hidden regulatory mechanism, a counterintuitive force for order within the apparent chaos. Yet, in a different scenario, the magnetic field might play the exact opposite role. As the galaxies churn and their fields are twisted and wound up by the differential rotation and shear flows, they can become a powerful source of turbulence. This magnetized turbulence acts like a cosmic whisk, violently stirring the gas, preventing it from settling into a calm, ordered collapse. This enhanced churning can actually promote the mixing of different gas clouds from each galaxy, efficiently homogenizing their chemical compositions far faster than gravity alone could manage. In this role, magnetism isn't a suppressant. It's a catalyst for complexity, ensuring the newly forged elements from supernova are thoroughly blended into the raw material for the next generation of stars and planets. The same fundamental force, depending on its strength and geometry, can either calm the storm or throw more fuel on the fire, making the outcome of any given merger even more difficult to predict. The monumental challenge, and the reason this remains such a profound mystery, is that observing these magnetic fields is extraordinarily difficult. We cannot see them directly. To map their invisible architecture, astronomers must use specialized radio telescopes equipped with polarimeters. These instruments detect the faint radio emission from electrons spiraling at nearly the speed of light along the magnetic field lines. The polarization of this light, the specific direction its waves vibrate, betrays the orientation of the field itself. It is a painstaking, time-consuming process, and so far, only a handful of the nearest merging galaxies have been studied in this kind of detail. Each one reveals a unique and complex magnetic personality, suggesting that we have merely scratched the surface of a vast and varied phenomenon. Without these direct observations, our computer simulations, no matter how sophisticated, are operating with a critical piece of the puzzle missing, trying to guess the rules of a game we can only partially see. This compelling mystery forces a fundamental shift in our perspective. We can no longer view a galaxy collision as a simple gravitational n-body problem. It is a multi-physics event of breathtaking complexity, a system where gravity, hydrodynamics, radiation, thermodynamics, and magnetohydrodynamics all interact across scales from the galactic to the atomic. The magnetic dimension is not a minor detail, it is an integral player in this cosmic orchestra. Its influence, whether by stifling star birth or seeding chaos, adds a profound layer of nuance to the secret histories of these embraces. To truly understand the story written in the stars, we must now also learn to read the lines of force written in the void, the invisible threads of magnetism that silently guide the fate of colliding galaxies. But the grand finale of this cosmic drama, the merger of the supermassive black holes themselves, promises to unlock an entirely new sense with which to observe the universe. When these two gravitational Goliaths finally spiral into one another, they don't just create a flash of light or a burst of radiation. They shake the very fabric of space-time, sending out ripples that travel across the cosmos at the speed of light. These are gravitational waves, and they represent a completely different messenger from the universe, one that carries pristine information about the most violent events, unaltered by matter or magnetic fields. For decades, our view of the cosmos has been limited to what we can see across the electromagnetic spectrum, from radio waves to gamma rays. But with the dawn of gravitational wave astronomy, we are now learning to listen to the universe, to hear the deep bass notes of these colossal collisions that have been silent until now. The gravitational waves produced by the merger of stellar mass black holes, like those detected by the LIGO and Virgo observatories, are like the high-pitched chirps of the cosmos. But the merger of supermassive black holes, the kind that sit at the hearts of galaxies, generates a profoundly different signal. These events produce low-frequency gravitational waves, a deep, resonant hum that can last for years as the black holes slowly spiral inward. This hum is far too low for ground-based detectors to hear. The arms of those instruments are too short. To listen for this cosmic bass note, we must go to space. This is the primary mission of the Laser Interferometer Space Antenna, or LISA, a future observatory that will consist of 3 spacecraft flying in a giant triangular formation millions of kilometers apart, connected by lasers. By precisely measuring the tiny fluctuations in the distance between these spacecraft changes smaller than the width of an atom, LISA will be able to detect the passing of these gravitational waves, tuning into a frequency of the universe we have never before been able to access. The data encoded in these waves is a treasure trove of information. Unlike light, which can be absorbed, scattered, or distorted on its journey to us, gravitational waves pass through everything almost completely unimpeded. They will tell us not just that a merger happened, but the exact masses and spins of the black holes involved. The spin, in particular, is a crucial clue. If the black holes are spinning in alignment with their orbit, it suggests they grew steadily through the accretion of gas over time. If their spins are misaligned or chaotic, it points to a more violent history, perhaps built up through multiple, random mergers with other black holes from earlier galactic collisions. This is the hidden biography of these monsters, a story written in the dynamics of their final dance, waiting to be read in the waveform of the gravitational signal they emit. However, turning this promise into reality is filled with challenges and uncertainties. One of the biggest questions is simply how often these events occur. The rate of supermassive black hole mergers is a critical number that feeds into all our models, but it remains poorly constrained. Will LISA hear a steady chorus of mergers from across the universe, or will it detect only a rare, occasional event? The answer depends on how efficiently black holes overcome the final Parsec problem and how often galaxies themselves merge. Furthermore, the environment around the black holes could leave its own imprint on the gravitational wave signal. If the merger happens within a dense, gaseous environment or amidst a crowd of stars, these surrounding materials could exert drag, altering the black hole's in-spiral and subtly changing the signal we receive. Disentangling these environmental effects from the pure signal of the black holes themselves will be a major focus for theorists and observers alike. The successful marriage of gravitational wave astronomy with traditional electromagnetic observations will mark a true revolution, a multi-messenger astrophysics on the grandest scale. Imagine LISA detecting the gravitational wave signal from a supermassive black hole merger in a distant galaxy. This alert would then be sent out to astronomers around the world, who would turn every available telescope, optical, radio, X-ray, toward that patch of sky, searching for any accompanying flash of light or burst of radiation. Did the merger trigger a final, furious feast of gas, lighting up the nucleus as a quasar? Did it create a dazzling kilonova-like event from the surrounding accretion disk? Or did it happen in the dark with no electromagnetic counterpart at all? The answer will tell us everything about the conditions at the heart of that newly merged galaxy. By listening to the echoes of these cosmic collisions and simultaneously watching for their light, we will finally piece together the complete story of how galaxies are forged, from the initial gravitational embrace to the final, universe-shaking merger of their darkest hearts. But perhaps the most awe-inspiring aspect of this future event is the perspective it offers us right now. We are living in the prologue of this cosmic story, at a unique moment in time where we possess both the knowledge of what is to come and the technology to model it with incredible precision. This impending collision is not a distant, abstract concept. It is a specific prediction based on meticulous measurements of Andromeda's motion, a prediction that allows us to run thousands of virtual simulations to explore every possible outcome. We are the first generation of humans to know the ultimate fate of our galactic home with such certainty, granting us a privileged vantage point on deep time. This transforms our understanding of the cosmos from a static picture into a dynamic, evolving narrative in which we, for a fleeting moment, are both the audience and the narrators. The great embrace of the Milky Way and Andromeda is a future history written in the motions of the stars, a story of destruction and rebirth that will unfold long after our civilization is gone. Yet it is a story we are uniquely positioned to tell its opening chapters. From the brilliant ignition of starbursts to the universe-shaking merger of supermassive black holes, the secret histories of cosmic collisions reveal a universe in a state of perpetual, dynamic evolution, a place where destruction and creation are not opposites, but partners in a majestic, billion-year dance. These galactic embraces are the great architects of the cosmos, sculpting the elegant spirals and massive ellipticals we see today, seeding the void with the heavy elements essential for planets and life, and leaving behind faint, fossilized clues in stellar streams and ancient halos that allow us to reconstruct this epic past. Every time we peer into the heart of a merging system like the Antennae galaxies or study the serene aftermath of an old elliptical, we are reading a chapter in a grand narrative of transformation, a story written in starlight and gravity. Yet, for every mystery we solve, a dozen new questions emerge from the darkness, reminding us of the boundless complexity and beauty of the cosmos. We now understand the broad strokes of how collisions trigger star formation, but the precise regulation of these starbursts remains elusive. We have mapped the gravitational influence of dark matter, but its fundamental nature is still one of physics' greatest enigmas. We can simulate the merger of black holes, but the solution to the final Parsec problem continues to challenge our models. This endless cycle of discovery and inquiry is what makes astronomy so profoundly humbling and exhilarating. It constantly expands our knowledge while reminding us of our tiny place within the immense scale of space and time. This journey through the secret histories of galactic collisions ultimately changes our perspective, inviting us to look up at the night sky with new eyes. That faint, fuzzy patch of light that is the Andromeda Galaxy is no longer just a distant neighbor. It is a future partner in a dance that will reshape our own Milky Way. Every galaxy we see, whether a perfect spiral or a featureless ellipse, carries the scars and stories of its own violent past. We encourage you to carry this sense of wonder with you, to ponder these hidden narratives, and to share your own thoughts and questions in the comments below. The conversation about our universe is one we can all be a part of. If you've enjoyed this journey into the mysteries of cosmic collisions, don't forget to subscribe for more explorations into the deep